In the vast darkness of space, something extraordinary lurks, an enigma that defies the very fabric of the universe. A cosmic puzzle so strange it seems almost mythical. It looks like a pearl, a perfect ring of blazing stars encircling a hidden core, silent, untouched, and mysterious. This is Hoag's object. To the naked eye, it's a symmetrical masterpiece, glimmering like a jewel suspended in the blackness. Before we dive into this cosmic puzzle, let's take a moment to appreciate the scale of it all. This story is travelling across the globe, reaching you right now. I'm always curious to see our small planet mapped out in the comments, so let me know which part of the world you're joining this exploration from. And if you believe these cosmic stories are worth exploring, the best way to support our mission is by liking this video and subscribing for the next one. But look closer. Its shape challenges everything we thought we knew about galaxies. No bridges, no chaos, only eerie perfection. Scientists once believed galaxies were born from chaos, from swirling clouds and collisions. Hoag's object refuses that story. It stands alone, an unexplainable wonder whispering secrets about the universe that might forever remain beyond our grasp. Something this perfect? It threatens to rewrite cosmic history itself. Hidden amidst the vast, seemingly endless expanse of the universe, there exists a peculiar galaxy that challenges everything astronomers once believed about how galaxies form and evolve. Known as Hoag's object, this cosmic marvel appears almost unreal, a perfect luminous ring of stars surrounding a dense central core, with no apparent connections or bridges between the two. Its striking symmetry and eerie isolation have made it one of the most intriguing objects in the cosmos, prompting scientists to delve deeper into its nature and what secrets it might hold about the universe itself. Hoag's object stands out immediately because of its uncanny shape. From a distance, it resembles a pristine halo of brilliant white stars encircling a compact nucleus, with almost no signs of the chaotic, irregular features found in most galaxies. The central core is a dense, elliptical concentration of stars, roughly 100,000 light-years across, comparable in size to our Milky Way, yet it appears vastly different due to the surrounding ring. The ring itself is a luminous band of stars, gas and dust, stretching over hundreds of thousands of light-years, forming a perfect circle that appears almost artificially constructed from some cosmic artist's blueprint. What makes Hoag's object especially extraordinary is not just its surreal appearance, but the mystery of how such a galaxy could come into being. Traditional galaxy formation models suggest that galaxies develop through complex processes involving gravity, dark matter, and the chaotic accretion of gas and stars over billions of years. They tend to be irregular, spiral or elliptical, often showing signs of recent interactions or mergers with other galaxies. Not Hoag's object. It looks as though it sprang from a perfect symmetrical design, with little evidence of interruption or disturbance. One might wonder, what processes could lead to the formation of such a pristine ring around a discrete core? To understand why Hoag's object is so unusual, it's essential to look at the different types of galaxies we observe in the universe. Most galaxies, spirals like the Milky Way, ellipticals, irregulars, are messy, chaotic, and often show signs of interactions. They twist, collide, and distort, their structures shaped by gravity's relentless tug. Yet Hoag's object appears remarkably isolated, unperturbed by neighbouring galaxies, with no apparent signs of tidal interactions or mergers. Its isolation raises questions about its origins. How did this perfect ring come into existence? Was it formed by some unique process that no other galaxy experienced? Or is it a snapshot of a rare, transient stage in galaxy evolution? These questions have puzzled astronomers since the galaxy was first discovered. The galaxy was identified in 1950 by astronomer Alan Sandage and colleague Arthur Hoag, who noticed its peculiar shape during a survey. They marvelled at its unusual form, an almost perfect ring encircling a small elliptical core. Ever since, scientists have sought to decode its origins and understand what makes this galaxy so exceptional. One prevailing theory suggests that Hoag's object is a galaxy that formed through a process called a collisional ring galaxy event. In such scenarios, a small galaxy or a massive cloud of gas plunges through a larger galaxy, sending ripples through the galactic disk and triggering a burst of star formation arranged in a ring. However, Hoag's object lacks many features typical of collisional ring galaxies. Instead of visible signs of a recent collision, such as distorted shapes, tidal tails, or nearby interaction remnants, it appears remarkably symmetrical and peaceful. Another hypothesis considers the possibility that the ring formed through a process called accretion. Perhaps gas and dust from the galaxy's surroundings accumulated in a ring around the core, leading to the formation of new stars in a circular pattern. This process is known as polar ring formation and is observed in some galaxies. However, Hoag's object's ring is perfectly round and aligned with the galaxy's centre, unlike some polar rings which tend to be inclined at odd angles. Some astronomers have also speculated about the role of dark matter in shaping the galaxy. Dark matter, the mysterious substance that exerts gravitational pull but emits no light, is thought to make up about 85% of all matter in the universe. Its distribution influences galaxy formation profoundly. In the case of Hoag's object, scientists propose that it might be embedded within a dark matter halo that provides an unusual gravitational environment, helping to preserve the ring's symmetry. Yet, perhaps the most perplexing aspect of Hoag's object is its apparent stability. For such a perfect ring to exist for hundreds of millions or even billions of years, it must be in a state of delicate equilibrium. Any disturbance, such as gravitational interactions with other bodies, would likely distort or dissipate the ring. Its steadfast stability suggests that some internal or external mechanism keeps it intact, but the exact nature of this mechanism remains elusive. Adding to its enigma is the galaxy's stellar content. The stars in the ring are mostly aged, and their composition suggests they formed from gas that was expelled or accumulated a long time ago. Meanwhile, the core contains an older, more evolved stellar population, hinting that the galaxy's nucleus has a history perhaps spanning several billion years. This age difference reinforces the idea that the ring and core may have formed at different times, through different processes. All these features combine to make Hoag's object not just a fascinating object, but a cosmic conundrum. It defies the common patterns and models that explain how galaxies assemble and evolve. Its near-perfect symmetry, isolation and stability challenge the expectations set by our understanding of galactic dynamics. Instead of being a chaotic, interaction-driven archetype, Hoag's object represents a rare and mysterious class of galaxies that appear to have achieved a kind of perfect balance, an elegant cosmic sculpture seemingly out of place in the tumultuous universe. Where does this leave us in the quest to understand the universe? Hoag's object is like a puzzle piece that doesn't quite fit into the grand picture assembled by classical astrophysics. It hints at alternative pathways of galaxy formation, pathways that are perhaps more subtle and less common than the violent mergers and accretions that dominate our standard models. It suggests that the universe, in its vast complexity, can produce structures of staggering beauty and symmetry through processes we have yet to fully comprehend. Further exploration and observation are essential. With advanced telescopes peering deeper into space, astronomers hope to uncover more about the galaxy's dynamic properties, its stellar motions, its dark matter content, its gas and dust distributions. These data could unlock clues about whether Hoag's object is a rare cosmic coincidence or a testament to a different kind of galaxy evolution altogether. Hoag's object is a cosmic mystery that beckons us to look deeper, to question more profoundly how the universe constructs its most curious creations. It stands as a shimmering reminder that, even in the vastness of the cosmos, there are phenomena so perfect and peculiar that they seem almost surreal, an ongoing challenge to our understanding of the fundamental laws that govern everything we see and, perhaps, everything we have yet to discover. The story of Hoag's object begins in the early 1950s, a time when the universe was still hiding many of its secrets behind veils of mystery. It was a period marked by rapid advancements in astronomy, with new telescopes and photographic techniques constantly pushing the boundaries of what humanity could observe. Among the many astronomers scouring the skies, one name stands out in the history of Hoag's object: Arthur Hoag. Arthur Hoag was an American astronomer working at the Carnegie Institution of Washington's Department of Terrestrial Magnetism. A dedicated investigator of galaxies and cosmic structures, Hoag had a keen eye for unusual objects, often poring over photographic plates taken by some of the most powerful telescopes available at the time. These plates were essentially sonic booms for the mind, a snapshot of the universe in moments of its distant past, captured on glass and coated with light-sensitive chemicals. In the early part of 1951, Hoag was examining a series of photographs taken of the skies over the Palomar Observatory. The Palomar Mountain in California housed the Hale telescope, a behemoth of a telescope with a mirror 14 feet in diameter capable of capturing faint and distant objects with remarkable clarity. These photographic plates, part of a project to chart and classify galaxies, contained countless celestial features, but amidst this sea of data, Hoag's trained eye caught something extraordinary. On one particular plate, a faint but unmistakably strange ring-like structure was visible. The object, later labelled as Hoag's object, appeared to be a nearly perfect ring of stars surrounding a bright central core. What made it stand out was not just its symmetrical face-on appearance, but also its relatively smooth, well-defined shape amid a backdrop of more common irregular galaxies. It was as if this galaxy had been painted by a master artist, a circle floating serenely in the vast darkness, defying common galactic forms. Hoag was immediately struck by the object's peculiar morphology. It didn't resemble the spiral galaxies that were well understood at the time, nor did it match the more irregular or elliptical types that astronomers had catalogued. Its perfect ring was unlike anything he'd seen before. With a combination of curiosity and a sense of discovery tinged with scientific caution, Hoag took detailed notes and measurements of the object. At first, there was a temptation to dismiss this as an artifact, perhaps a photographic anomaly caused by dust on the lens or some defect in the photographic process. However, Hoag patiently reviewed multiple plates and examined the object with the best available techniques. The consistency across different photographs confirmed that Hoag's object was a genuine cosmic structure, not a trick of the camera. Once he verified its authenticity, the question arose: what was this strange ring? Was it just a chance alignment of stars or a chance superposition of two different structures? Could it be a distant galaxy in a peculiar stage of evolution? Or was it something more exotic, a new class of galaxy altogether? It was clear that Hoag had stumbled upon something extraordinary. To ensure no detail was missed, he collaborated with colleagues and used the telescopes at Palomar and Mount Wilson. The observations confirmed that the ring comprised stars much like those in our own galaxy, hot, young, and glowing brightly in the blue part of the spectrum. The core, meanwhile, was a dense, bright elliptical region, likely a spheroidal collection of older stars. The discovery sparked considerable excitement, but also many questions. How did such a peculiar galaxy form? Why was its ring so perfectly symmetrical? Did it evolve naturally, or was it the result of some mysterious cosmic event? The astronomical community was both puzzled and intrigued, instantly recognizing that Hoag's object defied simple explanations. Arthur Hoag's discovery wasn't just about spotting a strange galaxy. It was about capturing something that challenged the prevailing understanding of galactic formation. It was a cosmic puzzle, an enigma wrapped in a luminous ring, sitting quietly in the sky, waiting for others to unravel its secrets. Hoag himself was modest about his discovery. He catalogued it carefully, provided detailed descriptions, and shared his findings through scientific papers. Yet his name and the object he uncovered would forever be intertwined, as Hoag's object became one of the most iconic and mysterious galaxies ever observed, igniting curiosity and debate among astronomers for generations to come. Hoag's object is one of the most striking galaxies, easily recognizable by its symmetrical, unusual appearance. When observed through a telescope, its most notable feature is a nearly perfect ring of bright yellowish stars surrounding a dense spherical core resembling a jewel in an orb. The structure radiates a surreal harmony, marked by breathtaking symmetry. The core is a compact spheroidal region densely packed with older, redder stars. Its diameter is about 5,000 light-years, small compared to the large surrounding ring. These stars emit a warm glow, indicating an aged stellar population that has existed for billions of years, formed from remnants of earlier cosmic interactions. Encasing the core is a luminous, nearly perfect ring of blue-white stars, gas and dust, spanning about 30,000 light-years. This ring contrasts sharply with the reddish-yellow core. Its blue hue signals vigorous star formation, with young, hot stars lighting up the scene like space fireworks. Many of these stars are only a few million to a billion years old, clearly younger than those in the core. One of Hoag's object's most observable features is its symmetry. The ring is flawlessly circular, maintaining a nearly perfect radius around the core. Its shape appears so precise that it seems sculpted from cosmic artistry. No significant deviations or distortions are visible, just an unbroken, elegant circle. To the untrained eye, it appears almost unnatural, like a cosmic art installation or alien architecture. The galaxy's brightness and colour distribution offer further clues. The core emits a subdued, warm glow, while the ring shines brighter due to luminous young stars. The boundary between the core and the ring is sharply defined, with minimal warping or asymmetry, giving Hoag's object an almost geometric perfection, with its two components deliberately complementing each other. A faint, diffuse halo extends beyond the bright ring containing stars and gas. Though less noticeable, this outer region hints at a more complex history. Observations suggest stars and possibly intergalactic gas extending beyond the main structure, with the halo being faint and difficult to see without detailed imaging. Spectral analyses across various wavelengths, infrared, ultraviolet and radio, reveal additional features. In ultraviolet light, the ring glows more brightly, emphasizing hot young stars. Infrared observations show dust and older stars, providing insights into its mass and composition. Radio data reveal faint signals of neutral hydrogen gas mainly along the ring, indicating the galaxy still has raw material for star formation. Dynamically, Hoag's object appears stable and well-ordered. Its rotation shows a coherent motion. Stars in the ring orbit the core in near-perfect circles, helping maintain the structure over cosmic timescales. Spectroscopic studies show the core's stars move with velocities typical of a spheroidal elliptical component, while stars and gas in the ring rotate in a flattened disc-like manner. This orderly motion is remarkable. Unlike many galaxies with chaotic internal motions or signs of recent mergers, Hoag's object appears calm, as if in cosmic equilibrium. One of the most puzzling aspects is its apparent isolation. It exists in a relatively sparse region, with no obvious companions or signs of recent interactions. Many galaxies with rings or peculiar shapes owe their forms to gravitational encounters, collisions, or mergers. But Hoag's object seems to have formed its ring through mechanisms that remain unclear, due to a lack of nearby galaxies for recent interactions. In terms of global properties, its total mass is estimated at a few billion solar masses, primarily dark matter, stars, and gas. Its luminosity is fairly high. Most visible light comes from the ring, especially in ultraviolet and blue wavelengths. Its apparent magnitude is about 12, making it visible through medium-sized telescopes but too faint for naked eye observation. All these features create a portrait of a galaxy that appears almost too perfect, too symmetrical to be entirely natural. The luminous ring, dense core, and overall harmony pose a cosmic puzzle. How did it form? Why does it have such an orderly structure? And how does it maintain this delicate symmetry over billions of years? These observable features form the foundation for exploring deeper mysteries that challenge our understanding of galaxy formation and evolution. The origin of Hoag's object remains uncertain, fueling debates about whether it resulted from a collision or formed gradually through internal processes. Its symmetry and isolation suggest it has not experienced recent disruptive events. Its unique ring raises questions about the mechanisms behind such precise formation. Some hypotheses propose it could be a rare galaxy type, formed by specific cosmic events, or through internal dynamics without external influence. Its stability over long periods, despite the lack of recent interactions, complicates explanations. Understanding Hoag's object could shed light on galaxy formation in low-density environments, the nature of ring galaxies, and the role of dark matter in maintaining ordered structures. Continued investigations across multiple wavelengths and deeper analysis are essential to uncover its true nature. Its peculiar features encourage astronomers to explore new models of galaxy evolution, making Hoag's object not only a captivating sight, but also a key to unlocking fundamental cosmic mysteries. Hoag's object is not just another galaxy, it's a baffling anomaly that challenges our understanding of galaxy formation. Typically, galaxy formation is envisioned as a gradual process. Vast clouds of gas and dust coalesce under gravity, spinning and collapsing over billions of years to form structures like our Milky Way. This framework explains the diversity of galaxies, spirals, ellipticals, irregulars, and their evolutionary processes. Yet Hoag's object defies this narrative. What makes Hoag's object extraordinary is its perfect ring. a luminous, symmetrical circle of stars encircling a central elliptical core. The ring is a pristine, bright structure, seemingly frozen in time, with stars arranged with startling regularity. The core resembles a calm elliptical galaxy, but it's encased by this extraordinary ring, almost like a cosmic hula hoop glowing with young, hot stars. This juxtaposition puzzles astronomers and defies expectations about galaxy evolution. Most galaxy growth involves collisions, mergers, and gradual matter accretion. Spiral arms form from density waves in rotating disks, while ellipticals are often remnants of violent mergers. Rings of stars are usually transient, resulting from collision events that send ripples through disks or from bars funneling gas into rings, igniting star formation. But Hoag's object's perfect symmetrical ring appears to have formed without recent disturbance, making it unlike any model predicts. It looks clean, with no signs of recent collisions or gravitational tugs that could explain its structure. Standard collision-based models can produce ring galaxies like the Cartwheel Galaxy, but these tend to be asymmetrical, disturbed, and show signs of violent interactions: tidal tails, star formation hotspots, debris trails. Hoag's object, by contrast, is remarkably tranquil, with its ring encircling a gentle, bulge-dominated core without distortion. This suggests a formation process that doesn't fit neatly into known violent collision scenarios. Even more perplexing is the scale and symmetry of Hoag's object. Its ring is well-defined and circular, implying a stable gravitational environment maintained over billions of years. Something standard models struggle to explain. How does a galaxy manage to form such a perfect ring without ongoing disturbance? Usually, such structures are transient, dispersing over cosmic timescales due to gravitational influences or interactions. Yet Hoag's object seems stable and ancient, like a cosmic jewel preserved in pristine condition, hinting at an alternative origin story still under investigation. Adding to the mystery is its environment, a low-density region of the universe, a quiet neighborhood where galaxies are relatively isolated. Such isolation suggests few interactions with other galaxies, raising questions about how the ring formed. Could it have resulted from gentle, gradual gas accretion or a faded merger? The evidence doesn't fully support these explanations. Some scientists have proposed more exotic ideas, such as the ring forming from dark matter interactions or gravitational effects involving unknown entities. Others speculate a rare, slow process, perhaps a dense gas cloud settled into a perfect ring, sparking star formation that became frozen in time. No single theory currently explains the phenomenon fully, as data remains inconclusive. The age of the galaxy also raises questions. When did the ring form? If as old as the core, billions of years, it must have maintained its structure despite cosmic turbulence. If younger, what events sparked its creation? Conventional models suggest such perfect rings are transient, resulting from recent collisions or accretion phases. The fact that Hoag's ring is so well preserved and appears stable over cosmic timescales suggests a formation mechanism, unlike known processes. Hoag's object highlights that the universe still holds phenomena challenging our understanding. It urges astronomers to rethink galaxy formation and evolution, considering roles for dark matter, gravitational anomalies, and other unseen forces. Could some hidden physics be involved? Might there be undiscovered mechanisms for forming such perfect rings without violent upheavals? Ongoing observations with advanced telescopes and simulations continue to probe Hoag's object. It remains a cosmic enigma, forcing us to question whether our current models are comprehensive or if critical pieces of the cosmic puzzle are missing. Despite its beauty and symmetry, Hoag's object asks a profound question. Are our theories complete, or are we overlooking fundamental physics that can produce such a serene, perfect structure amid the chaos of the universe? This galaxy is not just a passive object, but an active challenge, an invitation to open our minds, question established notions, and remain curious about the universe's deepest mysteries. It exemplifies how much remains to be learned about the grand cosmic dance that shapes all galaxies, including the one we see in our night sky, the enigmatic Hoag's object. Studying peculiar galaxies like Hoag's object isn't just about marveling at something bizarre in the cosmos, it's about unlocking the secrets of the universe itself. These extraordinary formations challenge our understanding of how galaxies form and evolve, forcing astronomers to question long-held theories and look for new explanations. When a galaxy defies typical behavior, like Hoag's object, with its perfectly concentric rings and mysterious nucleus, it serves as a cosmic puzzle piece that could potentially reshape our entire picture of galactic dynamics. One of the fundamental reasons to study these unusual galaxies is their rarity. They are not the common, sprawling spirals or massive ellipticals we see most often. Instead, they are oddities, locked in unique configurations that do not fit neatly into the conventional models of galaxy classification. By examining these outliers, scientists are essentially pulling back the curtain on the possible pathways that galaxies can take. Those pathways might be rare, or they might be more common than we think, hidden behind the veils of cosmic time, or only visible under specific conditions. There's also a deeper, more philosophical aspect at play. Peculiar galaxies might be the remnants of cosmic collisions, unusual mergers, or even the remains of galaxies torn apart by dark matter's gravitational grip. They act as natural laboratories for understanding the forces at work in our universe. For instance, Hoag's object's nearly perfect ring hints at a tumultuous past, perhaps a cataclysmic encounter with another galaxy that left behind this seemingly harmonious structure. Unraveling that history helps scientists piece together how galaxies grow, interact, and sometimes completely transform over billions of years. Furthermore, these galaxies might hold clues about the distribution of dark matter, one of the most elusive components of the universe. Since dark matter doesn't emit, absorb, or reflect light, its presence is inferred through gravitational effects on visible matter. Peculiar galaxies, with their strange shapes and motions, can reveal how dark matter is distributed on galactic scales. For example, if a ring galaxy like Hoag's object rotates in a way that can't be explained by visible stars alone, it signals that unseen dark matter is influencing its behavior. These insights can refine our models of dark matter's role in cosmic evolution, a question that remains one of the biggest mysteries in physics. Studying these uncommon galaxies also has technological implications. Observing and analyzing their complex structures push the boundaries of what our telescopes and instruments can do. High-resolution imaging, spectroscopic analysis, and computer simulations need to work in tandem to unravel their secrets. This technological push drives innovation, leading to better sensors, data processing algorithms, and even new theories of gravity or matter that might one day explain not just the peculiar galaxies, but the universe at large. Beyond scientific curiosity, examining such galaxies sparks a sense of wonder and perspective. They remind us just how vast, varied, and unpredictable the cosmos is. These objects challenge the notion that the universe is predictable or uniform, something that every astronomer and astrophysicist grapples with. They serve as vivid illustrations that our understanding is still incomplete, that the universe often surprises us in the most magnificent ways. Ultimately, peculiar galaxies like Hoag's object stand as cosmic beacons, illuminating the unknown. They compel us to refine our theories, develop better technology, and expand our knowledge about the fundamental workings of the universe. Each of these strange shapes is a story, a chapter in the grand narrative of cosmic evolution, and by studying them, we continually push the boundaries of what we know, bringing ourselves one step closer to understanding the true nature of reality itself. Hoag's object is an extraordinary galaxy whose structure defies typical classifications. Its most striking feature is an almost perfect ring, a luminous circle of stars that appears to float in space. Surrounding this stellar ring is a dense, luminous core, which acts as a celestial anchor. The core isn't just a small nucleus, it's a substantial, bright sphere filled with stars and gives the galaxy its glow. Peeling back its layers reveals a remarkably symmetrical design, an almost perfect circle of stars encircling a bright, compact nucleus. The ring stretches across a significant portion of the galaxy, arranged in a harmonious dance rarely seen elsewhere. Its symmetry and simplicity resemble a perfect ring-shaped jewel set against the dark velvet of space. The composition of the ring primarily includes young, hot stars, giving it a bluish hue observed in detailed images. Their presence indicates recent or ongoing star formation, which is unusual for galaxies of this type. Within the ring, clusters of stars are tightly packed but maintain enough spacing to form a smooth, unbroken circle. These stars follow a coherent circular pattern, illuminating the galaxy with hypnotic regularity. Moving inward from the ring, the galaxy's core is a dense sphere of older, redder stars. It acts as an inner hub around which the ring gracefully spirals. Unlike the lively ring, the core contains predominantly mature stars that have exhausted their nuclear fuel long ago. Its high stellar density hints at intense gravitational forces, yet it appears comparatively tranquil, a stark contrast to the active ring. The core and the ring are intimately connected through gravitational forces, creating a balanced, stable structure that has endured for billions of years. This stability makes Hoag's object so fascinating. The galaxy's architecture has remained remarkably unchanged over cosmic timescales, indicating a delicate equilibrium maintained by its unique formation. Beyond stars, observations suggest dark matter subtly influences the galaxy's structure. Though dark matter doesn't emit light, its gravitational effects are crucial, especially in maintaining the ring's stability. The distribution of stars, particularly in the ring, implies dark matter might provide unseen scaffolding that prevents the ring from dispersing into space. The galaxy's structure resembles a celestial donut, a perfect circle of bright stars encasing a glowing core. Its geometry is so precise that it appears almost crafted by an unseen hand. This symmetry and purity have sparked countless hypotheses about its origins and evolution. One compelling aspect is the ring's apparent isolation. It doesn't seem to be interacting or merging with a nearby galaxy, nor does it show signs of recent collisions. This suggests that its formation was a self-contained process, an event or series of events leading to its current shape and stability. Scientists have long pondered how such a structure could form naturally. Several theories have been proposed. Some speculate the galaxy's ring resulted from a past collision with a smaller galaxy, with the gravitational upheaval triggering star formation along a ring-shaped region. Others propose that internal processes, where the galaxy's angular momentum caused stars and gas to settle into a symmetric ring, might be responsible. Another intriguing hypothesis involves a massive black hole lurking in the core. Such an object, if it exists, could have played a role in channeling material into a ring-like formation or maintaining the ring's stability over billions of years. Although direct evidence of a black hole in Hoag's object remains elusive, its potential presence fuels debates and further research, since understanding the core is key to unraveling its history. Furthermore, some astronomers consider the influence of cold gas streams, vast flows of gaseous material falling into the galaxy from the cosmic web. These streams could have accumulated in a ring, sparking new star formation along its circumference. Over time, these clusters of young stars would brighten the ring, making it the prominent feature observed today. This scenario emphasizes the dynamic, ever-changing universe where cosmic filaments act as arteries feeding galaxies and influencing their internal architectures. Despite these hypotheses, no single explanation has been definitively proven. The symmetry, isolation, and age of Hoag's object challenge our understanding of galaxy formation. It remains a cosmic anomaly, a puzzle piece that doesn't fit neatly into conventional frameworks of galactic evolution. Its pristine symmetry hints at an elegant cosmic blueprint, one that mathematicians might envy. The galaxy has persisted in its current form for billions of years, prompting questions about the delicate balance between gravitational forces, star formation, and the cosmic environment. How did it come to be so beautifully arranged? Was it a chance cosmic coincidence, or the result of slow, gentle processes unfolding over eons? Whatever the case, Hoag's object offers a rare glimpse into the universe's capacity for both chaos and order. Continued study using advanced telescopes and computational simulations is uncovering more clues about its hidden secrets. Each new piece of data adds to the intricate puzzle of its formation, revealing that the universe's most beautiful structures are often also the most mysterious. Hoag's object stands as a testament to cosmic wonder, reminding us that even in an age of science, some phenomena challenge our understanding, urging us to observe more, question deeper, and marvel at the universe's creativity. Its structure isn't just a fascinating anomaly, it's a cosmic invitation to question assumptions, explore astrophysical boundaries, and ponder the universe's grand design. The symmetric ring and dense core are more than mere features. They symbolize the universe's artistry, crafted in chaos yet maintained in harmony. Studying Hoag's object brings us closer to understanding the universe and emphasizes how much remains beyond our reach. Its stories are written in the stars, beckoning us to listen and learn. At the heart of Hoag's object lies a luminous, densely packed core that appears almost like a miniature galaxy within a galaxy. This core is studded with countless stars, glowing intensely against the backdrop of the universe, and it is remarkably spherical in shape. Its brightness is a testament to the high concentration of stellar material packed into this compact region, which likely houses older stars that have been part of the galaxy's structure for billions of years. This central hub serves as the gravitational anchor around which the galaxy's other features dance. Encircling this core is the defining feature of Hoag's object, a perfect luminous ring composed of myriad bright stars, gas and dust, arranged in a near-perfect circle. This ring is not just a simple band of stars, it's a dazzling blend of stellar populations, with some regions glowing more brightly, suggesting recent or ongoing star formation fueled by the interstellar gas and dust sprinkled throughout its circumference. The symmetry of this ring is mesmerizing, precise, almost unnatural, raising questions about its origin and stability over cosmic timescales. The ring itself isn't a flat, featureless band, but exhibits subtle variations in brightness and color. These variations hint at the presence of different generations of stars, some older, more evolved stars that have exhausted their nuclear fuel and fade into a reddish glow, contrasted with younger, hotter stars that burn with bluish hues. This diversity hints at a dynamic history, possibly involving past interactions, mergers, or accretion events that replenished the star-forming material in the ring. Connecting the core and the ring is an intermediate region where the two components seem to blend, creating a smooth transition rather than a stark boundary. This zone is less well defined, possibly indicating a gravitational or evolutionary link between the dense nucleus and the sprawling stellar ring. As if the galaxy is a carefully choreographed cosmic ballet, each component plays its role in maintaining the overall symmetry and integrity of this extraordinary structure. Beyond the main ring, the galaxy's environment is surprisingly clean. There are no extensive spiral arms or flares typical of many other galaxies. It appears somewhat isolated, standing apart as a solitary oddity amid the vastness of space. This isolation might be a clue about its formation history, hinting that the galaxy did not form through the typical hierarchical mergers or spiral accretions that shape most galaxies. Instead, perhaps its unique morphology resulted from a more unusual, less understood process. Another notable aspect is the faint halo that surrounds the entire structure. This halo contains dark matter, an invisible, mysterious component that provides the extra gravitational pull necessary to hold the galaxy together and maintain its structure against disruptive forces. While dark matter can't be seen directly, its presence is inferred through the galaxy's gravitational effects on its visible components and the motions of its stars. The overall shape and composition of Hoag's object suggest a delicate equilibrium. The symmetry of the ring, the concentrated core, and the surrounding halo create a pattern that seems almost too perfect to have arisen by chance. This harmony hints at underlying physical processes that might have stabilized this marvelous structure over billions of years. Yet the precise mechanism that produced such a perfect ring-shaped galaxy still remains a matter of intense debate among astrophysicists. Scientists continue to study these components, trying to piece together the galaxy's history. Is it the remnant of a collision with a smaller galaxy that dislodged stars into a ring? Or did the galaxy form through a rare event involving the accretion of gas that settled into a stable ring? Or perhaps, more exotically, does it owe its existence to some as yet understood gravitational or dark matter phenomenon that stabilized the ring and kept it intact over cosmic epochs? Despite these mysteries, what is clear is that Hoag's object's morphology stands as a testament to the universe's capacity for bizarre, beautiful complexity. Its dense core, luminous ring, transitional zone, and surrounding halo form a portrait of cosmic artistry, an object that not only challenges our understanding of galaxy formation, but also invites us to look deeper into the forces shaping the universe. Each component, from the bright nucleus to the shimmering ring and the unseen dark matter holding it all in balance, contributes to a celestial sculpture that captivates scientists and stargazers alike, reminding us how much there is still to learn about the grand design of the cosmos. Hoag's object isn't an ordinary galaxy with a ring, it's a pristine celestial object that stands out from typical ring galaxies. Unlike most ring galaxies, which often result from dramatic gravitational interactions or collisions, Hoag's object appears almost untouched by such chaos. Its defining feature is a luminous, radiant ring encircling a dense, central core, forming an almost perfect circle that seems deliberately engineered. Most ring galaxies originate from violent events, galactic collisions that send streams of stars and gas outward, creating chaotic asymmetric loops. These encounters distort the galaxy's shape, producing irregular rings, tidal tails, and starburst regions. Their rings tend to be incomplete or asymmetrical, remnants of tumultuous encounters scattering cosmic debris into arcs and loops. These features are often jagged, with intense star formation triggered by collisions, resulting in chaotic, mesmerizing appearances. In contrast, Hoag's object appears pristine, like a jewel in the universe. Its ring is flawlessly symmetrical, unbroken, and perfectly circular. Sitting at the center is a dense spheroidal core, likely a small elliptical galaxy, remarkably stable with little evidence of recent disruption. The perfect roundness of the ring suggests a different origin, perhaps a more subtle, elegant process that does not involve recent collisions or violent interactions, but a gentler mechanism. Another key difference is internal dynamics. Collisions and mergers often leave galaxies with chaotic motions, gas turbulence, and uneven star formation. Hoag's object, however, exhibits calm symmetry. Its ring contains young, bright stars forming a precise circle, while the core remains dense with older stars, possibly formed earlier. This indicates a state of long-term stability and equilibrium, rarely seen in chaotic ring galaxies, highlighting its structural preservation over time. Stellar populations further distinguish Hoag's object. Typical ring galaxies show active star formation both within the ring and throughout the galaxy, fueled by recent inflows of gas and collision debris. They glow brightly in ultraviolet light, reflecting turbulent pasts. Hoag's object's ring also glows brightly, but its star formation is well regulated. Stars form within a thin, stable ring with minimal signs of widespread gas flows or turmoil, implying a peaceful, sustained process. Its morphology and origins set it apart further. Many scientists believe Hoag's object could be a relic of early cosmic conditions, formed through unique processes. Some theories suggest the ring resulted from gradual gas accretion along a stable orbit, possibly guided by dark matter or shaped by gravitational resonances. Others propose it formed from a gentle merger event so precise that the structure remained unperturbed and symmetrical, unlike the often tumultuous aftermaths seen in other galaxies. Its uniformity hints at a different evolutionary path from typical ring galaxies, which tend to be transient, dissolving or changing over cosmic timescales. Hoag's object's elegant symmetry suggests long-term stability, maintained over billions of years. This stability implies a delicate balance of gravitational, rotational, and possibly dark matter influences that have preserved its pristine form. Additionally, its size and mass distribution differ notably from other ring galaxies. The ring measures hundreds of thousands of light-years across and is densely packed with young stars. The central core, compact yet massive, acts as an anchor, balancing the structure. The gravitational relationship between the core and the ring maintains a stable, harmonious configuration. This contrast with often asymmetrical, clumpy structures seen elsewhere emphasizes its uniqueness. In many ways, Hoag's object resembles a carefully crafted cosmic sculpture, an object of purpose and precision amid the chaos of galaxy formation. Its symmetry isn't the product of violent upheavals, but likely long-term gravitational orchestration. It challenges our understanding of galaxy evolution, suggesting peaceful processes can create extraordinary structures of order and harmony in the universe. Instead of chaotic origins, Hoag's object presents a scenario of beauty through stability, an almost surreal arrangement prompting questions about the universe's innate capacity for order amid chaos. Its striking symmetry embodies cosmic harmony, hinting at principles of formation and persistence that may record early universe conditions. It suggests that, under certain circumstances, nature can produce structures of breathtaking beauty, defying expectations of cosmic chaos. Hoag's object invites reconsideration of galactic formation processes. Its existence implies paths to stability and symmetry different from tumultuous histories. Its elegance and symmetry serve as a testament to the universe's potential for order, even in environments often characterized by chaos. Overall, Hoag's object stands apart because of its near-perfect symmetry, stable structure, and peaceful formation history. It's not just a galaxy with a ring, but a cosmic anomaly, an extraordinary example of how elegance can emerge from the universe's complex gravitational dance. It challenges conventional ideas and inspires questions about galaxy formation and cosmic order. Its contrast to typical ring galaxies underscores the universe's diversity and capacity for harmony, blending beauty and stability in a way that continues to captivate astronomers and explorers alike. The appearance of Hoag's object challenges our existing models of galaxy formation in surprising and perplexing ways. When astronomers first discovered this cosmic marvel, they realized it defied the neat, predictable patterns typical of galaxy evolution. Instead of sprawling, irregular shapes or majestic spirals, Hoag's object features a nearly perfect, luminous ring encircling a dense, spherical core, like a cosmic hula hoop around a solitaire ball. Its symmetry appears almost unreal, challenging the chaos usually associated with galaxy formation, which tends to be messy and turbulent. Traditional models suggest galaxies form through gas cloud collapse, gradually developing structures like spiral arms or elliptical shapes over billions of years. These models predict asymmetry and irregularity, especially during early stages or after disruptive events like collisions. However, Hoag's object seems to have achieved an almost unnatural balance on its own, an almost perfect symmetry that doesn't align with these linear evolutionary paths. Its main body appears surprisingly undisturbed, as if frozen in time after reaching a stable configuration, even though such a perfect ring should be inherently unstable under gravity. One wonders how such an elegant ring could form and persist without collapsing inward or dispersing. The standard scenario for ring galaxies involves a smaller galaxy passing through a larger one, creating ripples and wavefronts that eventually form a ring. But Hoag's object shows no signs of such an interaction. No obvious companion galaxy, debris trails, or distortions suggesting recent collision. Its ring is so smooth and evenly luminous that it looks like a ribbon of stars, gas and dust orbiting in harmony around the core. The core itself presents a puzzle. It's a dense, spheroidal concentration of stars that resembles a miniature elliptical galaxy. In many models, such dense centers result from gradual accumulation over cosmic time, often bearing scars of past mergers or accretion. But in Hoag's object, the core remains compact and undisturbed, as if it were a relic from another era, a survivor that slipped through galactic evolution with minimal interactions. Its presence raises questions about how such a dense, isolated core can remain undisturbed for so long in a seemingly symmetrical galaxy. This challenges our understanding of dark matter's role in shaping galaxies. Many theories posit that dark matter halos influence galactic morphology profoundly. The symmetry of Hoag's object suggests a dark matter halo that's equally symmetrical, providing a stabilizing framework for both the ring and core to maintain their shapes over billions of years. Yet the very existence of such a perfect stable ring pushes the limits of gravitational equilibrium theories involving dark matter. It raises the possibility that this galaxy formed within an unusually symmetrical dark matter halo, a rare cosmic event, or that entirely different processes are at work. Some astrophysicists propose that Hoag's object might have formed through the accretion of gas from the intergalactic medium, gas that settled into a ring under the influence of the galaxy's gravity and angular momentum. However, mechanisms behind such a process would have to be extraordinarily precise to produce a perfectly symmetrical, stable ring over cosmic timescales. The ring's smoothness and consistent brightness seem to require cosmic fine-tuning, which is difficult to reconcile with the chaotic nature of galaxy formation. Additionally, the galaxy's stability suggests that galaxy formation processes are more diverse than previously thought. It hints that some galaxies could form through mechanisms outside the conventional models, possibly through rare, finely balanced cosmic events, or as a consequence of unique initial conditions early in the universe. Hoag's object might be an exceptional case, proof that the universe can produce structures that challenge our understanding, urging us to rethink standard narratives of galaxy formation and evolution. In essence, the symmetry and apparent tranquility of Hoag's object serve as a stark reminder that the universe still holds many secrets. Its existence defies the predictive power of current models, encouraging scientists to develop new theories or refine existing ones. Whatever its origin, Hoag's object exemplifies the universe's uncanny ability to produce seemingly impossible structures, prompting a continuous re-examination of what we believe about galaxy genesis and persistence across cosmic epochs. It's as if the galaxy itself is a cosmic puzzle, a shining enigma at the frontier of astrophysics, whispering that much remains to be discovered about the universe's grand architecture. Hoag's object isn't just any galaxy. It's a cosmic rarity that challenges our understanding of galaxy formation and evolution. What makes this galaxy stand out at first glance is its nearly perfect, luminous ring of stars encircling a dense elliptical core, as if a cosmic artist carefully painted it into space. Unlike most galaxies with irregular shapes, spirals, or chaotic dust lanes, Hoag's object boasts a surreal symmetry, an almost perfect circle floating in the universe. This symmetry isn't merely aesthetic, it hints at something fundamentally unusual about its history. Most galaxies undergo chaotic interactions, bouncing, colliding, and developing spirals or irregular forms over billions of years. Hoag's object, however, appears untouched by such chaos. Its ring seems stable and long-lasting, composed of young, bright stars shimmering with a bluish hue reminiscent of stellar nurseries. Meanwhile, its core emits a softer, yellowish glow, indicating an older stellar population that has quietly simmered in the galaxy's center for billions of years. The ring itself consists of thousands, perhaps millions, luminous stars. This isn't just a scatter of stars, but a coherent, well-defined ring that appears to have maintained its shape for millions of years. Its perfect symmetrical form raises questions about stability. How can such a fragile-looking structure remain pristine over cosmic timescales? One of Hoag's object's most astonishing features is its relative isolation. It sits apart from crowded galaxy clusters. Without neighboring galaxy interactions or gravitational tugs, how did this structure form? Was it an ancient collision? Did a massive gas cloud self-organize into a ring? Or perhaps unseen forces like dark matter played a crucial role? Its isolation makes it an ideal case for understanding galaxy formation without external influences. Another peculiarity lies in its rotation. Observations show the core and ring rotate around a common center, but their dynamics suggest the ring moves somewhat independently, like a cosmic ring fence, gravitationally linked but maintaining its own rhythm. This hints at a complex history and raises questions about how material was redistributed to form this perfect circle. Beyond shape and composition, Hoag's object offers insights into the universe's past. The stellar populations tell stories, young stars in the ring indicating recent or ongoing formation, older stars in the core reflecting long-term stability. The proximity of these distinct populations is puzzling. What triggered star formation in this perfect ring? Was there a past collision that sent gas swirling into a ring, or an unusual gravitational event that funneled matter into a circular shape? Adding to its intrigue, astronomers have detected hints of a faint outer shell or halo surrounding the galaxy, a ghostly remnant of its turbulent history. Whether this halo results from past mergers or the accretion of smaller satellite galaxies remains debated. These features suggest Hoag's object may not be as isolated as it seems. It could have a more complex history involving minor mergers or interactions that are now largely faded from view. The galaxy also lacks dust lanes or gas clouds typically associated with star-forming regions in spirals. Its surface appears remarkably clear, with predominantly stellar populations. This emptiness hints at an unusual life cycle. Perhaps it formed in a dust-free environment or shed or consumed much of its gas over time, leaving behind the bright stars observed today. All these features, the near-perfect symmetry, the separate core and ring, stellar populations, isolation, and stable morphology, render Hoag's object an enigma. It defies standard classifications laid out by Hubble's tuning fork and challenges existing models of galaxy growth. Usually, galaxies develop arms through density waves, spiral out via gravitational interactions, or form through accretion of smaller systems. Hoag's object seems to have avoided these processes or experienced them uniquely, leaving only this pristine ring, almost like cosmic artistry. Its implications for dark matter are profound. Dark matter's elusive influence in galaxy formation suggests it might have played a key role in creating and maintaining this ring's structure. Could dark matter's distribution be responsible for the stability of its perfect circle? This question makes the galaxy an ideal laboratory for testing dark matter theories and galactic dynamics. The more scientists study Hoag's object, the more it appears to be a key to unlocking new astrophysical paradigms. Its peculiar features might reveal rare, perhaps even unique, cosmic events under specific conditions, or it may offer a glimpse into a stage of galaxy evolution not previously observed. Whatever its origins, Hoag's object stands as a cosmic mystery. It invites astronomers to think beyond traditional models and consider new mechanisms of galaxy formation, stability, and architecture. It encourages us to see the universe as not just a place of recurring patterns, but as a canvas filled with extraordinary phenomena that push understanding further. Truly, Hoag's object isn't merely a beautiful shape in the sky. It's a doorway into the unknown, urging scientists to uncover stories hidden deep within the cosmos. Scientists have proposed various theories to explain Hoag's object, each aiming to understand how such an extraordinary galaxy could form and maintain its structure. It's akin to solving a cosmic riddle, with no single hypothesis gaining universal acceptance. These ideas range from cosmic collisions to dark matter influences, and even entirely new frameworks for galaxy evolution. One early theory suggested Hoag's object resulted from a colossal collision. In this scenario, a smaller galaxy might have passed through a larger one, causing gravitational shocks that ejected matter into a ring. This resembles other ring galaxies like the Cartwheel Galaxy, where collisions are believed to produce luminous gas and star rings. However, Hoag's object challenges this idea. It is symmetrical and undisturbed, with a smooth, dense core and a well-defined ring, indicating a calm, stable origin rather than a recent violent event. Another explanation involves resonant accretion, a process where the galaxy's core gradually accumulates gas and stars over billions of years. Gravitational resonances could have caused matter to migrate outward uniformly, forming a ring around the core. This is comparable to Saturn's rings, maintained by gravitational interactions with its moons. While this idea accounts for the galaxy's symmetry and stability, it raises questions about initial conditions, especially given the galaxy's apparent isolation. Hoag's object's tranquility is remarkable. Unlike galaxies resulting from interactions or mergers, it appears solitary. This led scientists to consider dark matter's role. Some theorize the galaxy is embedded within a vast spherical dark matter halo, an invisible mass exerting gravitational influence without emitting light. Such a halo could stabilize the luminous ring, preventing it from dispersing or collapsing inward. This aligns with understanding that dark matter dominates galaxy mass, influencing formation and stability. A sufficiently massive, well-distributed dark matter halo could create the gravitational environment needed for the ring's long-term stability. Some models propose that the dark matter halo itself might have a peculiar shape or uneven distribution, perhaps elongated or clumpy, influencing the formation of the ring through gravitational interaction. In this view, the luminous ring is the visible tip of a larger dark matter structure shaping the galaxy behind the scenes. The core might be a dense concentration of stars and gas that settled early, with the ring being an area where matter accumulated, maybe pushed outward by gravitational resonances or dark matter effects. Beyond gravity and collisions, more exotic hypotheses involve supermassive black holes or new physics beyond the standard model. Could the galaxy's active nucleus have expelled gas, creating the ring? Although no direct evidence shows an active nucleus, such a scenario isn't dismissed outright. For example, a dormant black hole might have expelled matter at high speeds, forming a shockwave that carved out the luminous ring. Though speculative, this fits with the galaxy's symmetry. Modified gravity theories also offer alternatives. Variants like modified Newtonian dynamics, MOND, aim to explain galaxy rotation curves without dark matter. In these models, altered gravitational forces at large distances could enable stable ring-shaped structures to form independently of dark matter halos. While controversial and lacking extensive observational support, these ideas demonstrate the innovative thinking prompted by Hoag's object's peculiar form. Some astrophysicists consider that Hoag's object might be a transient phase, an ephemeral galaxy in evolution. Perhaps it recently settled into a stable configuration after a turbulent past, or it's a long-lived anomaly. Its pristine symmetry hints at a quiet history spanning millions or billions of years. Spectroscopic analysis might uncover clues about its origin, whether from gradual accretion, internal resonances, or rare cosmic events. Another hypothesis combines multiple mechanisms. A past collision with a smaller galaxy might have disrupted the galaxy, with dark matter influences and internal resonances smoothing out the structure over time. Imagine a smaller galaxy passing through in the distant past, causing initial disturbances, which were then stabilized by dark matter. Internal dynamics could have evolved into the elegant ring observed today, an intricate cosmic process unfolding over billions of years. The core's properties also raise questions about age and composition. Spectroscopy indicates the core is mostly old stars, while the ring contains relatively younger stars. This layered pattern suggests a complex history, with early star formation in the core, followed by star formation in the ring from gas collected later. This layered formation adds complexity, implying multiple processes across different epochs contributed to the galaxy's structure. In attempting to synthesize these hypotheses, current understanding is that no single process explains Hoag's object fully. Its formation and stability likely involve interplay among dark matter influences, internal resonances, and perhaps some cosmic chance. The galaxy challenges existing models, prompting scientists to refine their theories. Research continues with high-resolution spectroscopy, detailed simulations, and new observations. Each step brings us closer to understanding how such a galaxy could form. Future technologies may allow us to trace the motions of stars in the ring or analyze its composition in detail, revealing its evolutionary history. This deeper insight could finally uncover the true recipe behind this cosmic masterpiece. Ultimately, Hoag's object highlights the universe's complexity. Even in a cosmos we've mapped extensively, phenomena like these remind us of endless mysteries waiting to be uncovered. Its perfect ring and silent elegance captivate scientists and stir curiosity about the fundamental processes shaping the universe. As our knowledge evolves, it continues to challenge assumptions, inviting further exploration. Its unique structure encourages us to think about galaxy formation in new ways, contemplating dark matter's influence, internal dynamics, past interactions, and modifications to gravity. It embodies scientific pursuit, an ongoing effort to decode the universe's secrets, fueling our desire to learn more. Each discovery pushes boundaries further, showing that even in space's vastness, secrets remain just beyond reach, beckoning us to keep searching. The galaxy's mysterious origin could involve multiple factors: collisions smoothed by dark matter, internal resonances shaping the ring, or external influences like past interactions. Its structure hints at a complex, layered history. The stellar populations tell a story, an ancient core of old stars with a surrounding ring of younger stars, indicating ongoing star formation, likely fueled by gas redistribution over time. This layered history suggests Hoag's object's formation was a gradual, multifaceted process. Different mechanisms could have worked together over billions of years, molding this extraordinary structure. No single model provides a complete explanation, but each adds a piece to the puzzle. The galaxy exemplifies how multiple forces, gravity, dark matter, internal dynamics, interact in shaping cosmic structures. The enigma of Hoag's object embodies the challenge and excitement of astrophysics. It pushes scientists to develop new theories and refine existing ones. As technological advances enable better data collection, our understanding will improve, potentially revealing its true past. Studying such galaxies offers broader insights into galaxy formation and evolution. In summary, current theories encompass a range of possibilities: collision remnants, resonance-driven structures, dark matter influences, black hole activity, modified gravity, and transitional states. Each hypothesis offers insights, yet none fully explains all observed features. Progress depends on integrating multiple mechanisms into comprehensive models that align with observations. Hoag's object remains a remarkable natural laboratory, showing that the universe holds diverse and mysterious phenomena. Its symmetry and stability challenge standard thinking, inspiring new ideas and investigations. Continued research promises to uncover its secrets, advancing our understanding of galaxy formation processes at a fundamental level. The story of Hoag's object reminds us that the cosmos is full of surprises. Its elegant ring demonstrates the complexity and diversity of galaxy structures, It also emphasizes that scientific inquiry is an ongoing journey, each discovery opening new questions. The galaxy invites us to keep looking, questioning, and exploring the fundamental forces shaping our universe. The idea that Hoag's object could result from a galaxy collision or merger sparks curiosity. Initially, one might imagine a cosmic clash, two galaxies colliding and leaving behind a perfectly symmetrical ring. But the reality is more complex, involving intricate processes and cosmic dances that challenge intuition. Envision a smaller galaxy streaking through space, drawn by gravity toward a larger galaxy. As it plunges into a crowded galactic neighborhood, or drifts alone, it might slowly spiral inward. During this collision, tidal forces stretch and distort both galaxies, creating streams of stars and gas that ripple outward like cosmic waterfalls. These tidal tails and bridges become raw material for new structures, potentially forming the luminous ring seen today. Collision scenarios often involve the formation of a ring galaxy. When a smaller galaxy passes close enough to a larger galaxy's core, gravitational effects cause density waves to propagate through the galaxy's disk. These waves resemble ripples in a pond, spreading outward and compressing matter. In the cosmos, such waves can trigger star formation, illuminating the ring with young stars. Over millions of years, these ripples can settle into a stable, bright ring, contrasting with the galaxy's dense core. The age and star distribution along the ring provide clues about collision timing. If populated with young stars, it suggests a recent collision where the gravitational disturbance sparked starbirth. Conversely, older stars imply the event occurred long ago, with the ring as a resilient, long-lasting structure. Yet stability is crucial. Ring structures formed by collisions are typically transient, dispersing or fading over hundreds of millions of years. But Hoag's object's luminous ring remains remarkably stable, hinting at a more nuanced collision history, or perhaps a different origin altogether. It might have resulted from a collision at just the right angle or velocity, creating an enduring ring, or from multiple minor mergers gradually building the structure. Reconstructing the galaxy's history involves detailed observations, analyzing star ages, their motions, and the distribution of gas and dust helps astronomers determine if a recent collision formed the ring or if it's a remnant of ancient events. Signs such as shock waves or disturbed gas kinematics support a collision scenario. Conversely, a serene environment might suggest an alternative origin. Merger scenarios add a different layer. Instead of a galaxy passing through another, two galaxies might slowly coalesce over cosmic time. If a smaller galaxy merges with a larger one, its stars and gas could form features like rings or shells. However, forming a perfectly symmetrical, luminous ring through a merger alone is challenging, especially without disturbing the galaxy's core or creating chaos. Some models propose that a merger can deposit a ring of stars in a stable orbit, provided the incoming galaxy approached at a specific angle and velocity. The remnant could settle into a configuration where the ring appears as a luminous feature encircling a spheroid core. But achieving the symmetry seen in Hoag's object is difficult. Merger remnants often display irregularities initially. Nonetheless, simulations suggest that over billions of years, internal dynamics might smooth out irregularities, leading to a symmetrical appearance. What makes collision and merger models compelling yet perplexing is that neither perfectly explains the galaxy's pristine symmetry and stability. Collision models depict waves rippling outward, triggering star formation and creating a luminous ring that can persist if conditions are right. But they struggle to explain the galaxy's largely undisturbed core. Ongoing collision signatures are not clearly observed. Merger models, meanwhile, often involve chaos and irregular features, signs that are not prominent in Hoag's object. Its symmetry and stability suggest a gentler evolution, raising doubts about whether such a calm, perfect ring results from violent interactions. Still, the universe doesn't always follow expectations, and hybrid theories have been proposed. Perhaps a merger triggered star formation, followed by a long period of quiet stability. Alternatively, a collision at the right angle and velocity might have produced a transient ring that evolved into the stable structure observed today. These models highlight how much remains uncertain about galaxy formation. Hoag's object might be a cosmic anomaly, born from rare, finely tuned circumstances. It exemplifies how violent interactions can sometimes produce serene beauty, challenging physics and our ideas of stability. Each hypothesis, each simulation, adds a piece to the larger puzzle, bringing us closer to understanding how such extraordinary galaxies form and evolve. They inspire ongoing research as astronomers seek clues in the galaxy's ring and core to unveil its history. In the end, Hoag's object persists as a cosmic mystery. Its formation, whether through collision, merger, or a combination, continues to be debated. Its remarkable symmetry and stability defy simple explanations, prompting scientists to explore hybrid scenarios and new models. As our understanding deepens, we recognize the galaxy as a testament to the universe's complexity. It challenges us to reconsider notions of chaos and order in galaxy evolution, highlighting that sometimes the most beautiful structures emerge from the interplay of violent and gentle processes across cosmic time. Dark matter and dark energy, these elusive components of our universe, are like cosmic ghosts whispering secrets about the shape and stability of galaxies, including Hoag's object. Its unique luminous ring encircling a dense core has challenged long-held ideas about galaxy formation. Could dark matter be the hidden architect behind this structure? Or is dark energy subtly influencing the universe's overall design to keep such formations stable over billions of years? Exploring these possibilities helps us understand the forces shaping Hoag's object. Dark matter, the unseen mass that neither emits nor reflects light, exerts gravitational pull affecting stars and gas within galaxies. In typical spirals, dark matter forms a halo that acts as gravitational glue maintaining integrity. For Hoag's object, this halo might be silently sustaining its symmetry. Its gravity could serve as scaffolding, ensuring the luminous ring remains stable instead of dispersing or collapsing inward, a fate some models suggest could happen. Imagine dark matter as invisible architecture, shaping cosmic structures, but only detectable through its gravitational influence. Its dominance could prevent the ring from diffusing, acting as a stabilizing force preserving the galaxy's striking shape over eons. Some scientists theorize that the galaxy's unusual form results from interactions or collisions of dark matter halos early in cosmic history, creating a gravitational niche where stars and gas are trapped in the ring. This might explain the carefully ordered stellar orbits around the core. The distribution and density of dark matter influence the galaxy's rotation curve, the way stars and gas move at different radii from the center. Typically, these curves are flat or rising at galaxy outskirts, defying expectations based solely on visible matter. In Hoag's object, studying its rotation helps determine the dark matter content and distribution. If the halo is symmetric or concentrated, it could explain its remarkable stability and symmetry. The balance between dark matter's gravitational influence and the visible structures could be what keeps the luminosity ring intact over cosmic time. Dark matter's role is complemented by dark energy, another mysterious force driving the universe's expansion. Dark energy acts like a cosmic anti-gravity, proliferating on the largest scales, galaxy clusters, voids, and intergalactic space. Although its influence on Hoag's object is indirect, it remains significant. As the universe expands, dark energy stretches space, impacting galaxy evolution and interactions over billions of years. It influences the rate at which galaxies move apart, affecting structure formation. Some hypotheses suggest dark energy played a role during Hoag's object's formation, either facilitating or impeding interactions that shaped its current form. In scenarios where galaxy interactions or accretion events shaped Hoag's object, dark energy's influence could have been crucial in determining how long those features remained stable. In a universe where dark energy causes galaxies to drift apart more rapidly, collisions and interactions that could disrupt such elegant structures might be limited. Conversely, where dark energy's influence is less dominant, these galaxies could retain their form longer, offering insights into the interplay between dark energy and galaxy morphology. Its subtle influence might help explain why Hoag's object remains so well preserved. Understanding the relationship between dark matter, dark energy, and Hoag's object is akin to decoding a cosmic blueprint. Though the galaxy displays visible stars, gas, and its luminous rings, it also hints at deeper invisible influences shaping its destiny. Its stability and symmetry suggest a delicate balance, dark matter providing the gravitational foundation, while dark energy subtly influences its evolution across cosmic epochs. Together, they form a cosmic dance that shapes large-scale structure and calls for deeper investigation. Studying Hoag's object reveals clues about the universe's unseen components. Its structure resembles a cosmic fingerprint, hinting at the distribution of dark matter and the influence of dark energy on large scales. Every observation unravels part of this mystery, pushing us closer to understanding these shadowy forces. They sculpt the universe on both grand and minute scales, revealing the intricate connections between visible matter and the unseen universe. In the grand story of cosmic evolution, dark matter could be the silent builder anchoring Hoag's luminous ring and core through gravity, maintaining its stability. Meanwhile, dark energy acts as the unseen artist, influencing the universe's expansion and galaxy stability. Their interplay forms a complex process, one that continues to challenge and inspire our understanding. Hoag's object is more than just a beautiful galaxy. It's a window into the profound forces shaping the cosmos, waiting for us to unravel its secrets and comprehend the deeper truths behind its formation. The enigmatic nature of Hoag's object has sparked interest beyond traditional explanations, inspiring alternative hypotheses that challenge the conventional understanding of galaxy formation and evolution. While mainstream models often focus on collision and accretion scenarios, these unconventional ideas open new avenues of thought, inviting us to ponder whether the galaxy's extraordinary structure might result from more exotic or overlooked processes. One hypothesis suggests Hoag's object isn't just a product of collision or accretion, but could result from stellar ring galaxy formation driven by gravitational influences from unseen or dark matter structures. If the luminous ring is due to gravitational lensing or dark matter interactions, it could imply the presence of large-scale cosmic filaments or massive dark matter halos, shaping the galaxy's form in ways we have yet to fully understand. Some scientists believe if dark matter behaves differently than predicted, it could exert gravitational forces creating stable stellar rings without recent interactions or disruptive events. Further, an unconventional idea involves cosmic colliders or universe-scale magnetic fields influencing galaxy morphology. Imagine a universe where magnetic forces are far more dominant than traditionally thought, capable of shaping and maintaining intricate ring-like structures over billions of years. In this scenario, the stability of Hoag's object's luminous ring might be due to powerful magnetic fields acting as cosmic sculptors, guiding gas and stars into precise circular formations. This challenges the idea that galaxy structures are primarily shaped by gravity, suggesting electromagnetic forces may play a more significant role under certain cosmic conditions. Some hypotheses involve the influence of an off-center supermassive black hole. Unlike typical galaxies with a black hole at the nucleus, some propose an asymmetric black hole, perhaps rogue or displaced due to gravitational interactions, that could influence matter's distribution in unusual ways. Such a black hole might generate gravitational waves or exert dynamical influences that help create and stabilize a stellar and gaseous ring around the core, even without recent collisions or accretion events. This pushes our understanding of black hole behavior and their influence on galaxy architecture. Other ideas are rooted in multiverse or higher dimensional theories. Could Hoag's object be a cosmic artifact resulting from interactions beyond our familiar three spatial dimensions? Some theorists propose our universe might intersect with other dimensions or branes, with gravitational or matter exchange manifesting as unusual galaxy structures. In this context, the galaxy's symmetry and isolation might be the result of higher dimensional processes, a cosmic mirage or interference pattern, inducing a pristine stellar ring without the typical chaos seen in galaxy formation. Another provocative concept suggests that what we observe might be a frozen or caught-in-transit shape, resulting from a phase transition in space-time itself. If space and time are subject to dynamic changes over cosmic timescales, Hoag's object could be a snapshot of a transient, stabilized state within cosmic evolution. Over unimaginably long periods, phase transitions might produce regions where matter naturally organizes into stable rings, defying classical galaxy models' expectations. Some scientists entertain the idea that Hoag's object isn't formed naturally, but is an extraterrestrial construct or artificial galaxy. Though speculative, it raises the question of whether an advanced civilization could engineer or influence galaxy-like structures. If so, the galaxy's symmetry and shape might be intentional, serving as a cosmic message or a form of galactic art rather than purely natural. All these hypotheses, though highly speculative and lacking definitive evidence, emphasize how Hoag's object challenges our understanding. It's a galaxy that refuses to fit neatly into existing models, prompting us to expand our thinking about the universe. Whether dark matter, Magnetic fields, black holes, higher dimensions, or extraterrestrial engineering, each idea pushes boundaries and stimulates curiosity about what other secrets the universe might hold. Hoag's object not only puzzles astronomers, but invites a re-evaluation of fundamental principles through which we interpret the cosmos, a reminder that the most beautiful mysteries often defy simple explanations, urging us to look deeper and think broader. In sum, alternative theories include dark matter influences, perhaps unseen filaments or halos, stabilizing the ring without collisions, magnetic fields on a cosmic scale sculpting the galaxy, an off-center supermassive black hole influencing matter distribution, higher dimensional interactions producing the galaxy's symmetry, phase transitions in space-time creating stable structures, and the possibility of an alien-engineered galaxy serving as a message or art. Each hypothesis, grounded in science or speculation, emphasizes the need to reconsider galaxy formation models and the universe's nature. Hoag's object continues to challenge and inspire, pushing the boundaries of what we know and daring us to explore beyond our current understanding. Its strange, pristine form invites ongoing investigation into cosmic forces working behind the scenes, perhaps more exotic, subtle, or unknown than we currently comprehend. As understanding advances, what is now speculative may become tomorrow's paradigm, transforming our view of this extraordinary galaxy and the universe at large. To determine the true nature of Hoag's object and evaluate the proposed models, astronomers have outlined several key observational tests. These aim to reveal whether its peculiar structure results from a collision, gradual accretion, dark matter influence, or internal dynamical processes. One initial step involves multi-wavelength imaging, optical, ultraviolet, infrared, and radio, mapping the galaxy's components. Optical images highlight the perfect ring and core, but other spectra reveal star formation rates, dust content, and cold gas and molecular cloud distribution. If the ring shows active star formation, while the core remains quiescent, this suggests recent gas accretion or specific evolutionary pathways. Conversely, a lack of new stars indicates an older, settled structure, possibly formed long ago through a collision, then stabilized over time. Next, astronomers analyze the galaxy's kinematic signatures by measuring star, gas, and dust motions via spectroscopy to assess velocity fields within the ring and core. Smooth, aligned rotation suggests a stable, self-gravitating structure that has matured. Turbulence, warps, or counter-rotation may indicate past interactions, such as collisions or mergers, implying external material has been captured and is settling into the galaxy's gravitational potential. Three-dimensional velocity mapping helps determine whether the ring is transient or long-lasting, crucial for understanding the galaxy's symmetry over cosmic timescales. Investigating dark matter distribution forms another critical test, since dark matter influences galaxy dynamics. Techniques like gravitational lensing and dynamical modeling estimate the dark matter halo properties. An unusually concentrated or peculiar halo might suggest dark matter played a role in forming or stabilizing the ring. A typical halo, however, would support models favoring internal processes or past interactions, rather than dark matter anomalies as the cause of the ring's formation. Stellar population analysis across the galaxy provides further insight. Spectroscopy reveals stellar ages, metallicities, and compositions in various regions. Uniform stellar ages across the ring could indicate a single formation event, such as a collision or gas accretion, creating the entire ring at once. Multiple stellar generations with varying ages and chemical signatures imply a more complex evolutionary history. If the ring hosts predominantly young stars while the core is older, external gas accretion triggering new star formation becomes plausible. Environmental factors also warrant examination. Is Hoag's object isolated, or are there faint satellites or debris indicating past mergers? Deep imaging surveys can detect tidal streams, stellar debris, or warped features, signs of recent interactions. The absence of such features argues against a collision, favoring internal evolution or slow accretion. Conversely, detecting faint streams or debris suggests recent or ongoing mergers or accretion events, challenging the idea of an isolated formation. Gas content and distribution are studied through radio observations, particularly at 21 centimeters, the neutral hydrogen line. The presence and arrangement of cold gas can indicate ongoing accretion, merger activity, or exhausted gas resources. Significant, isolated gas in a ring points to recent infall or active accretion. A dearth of gas supports models where the ring is a relic of an ancient event that has stabilized. The stability and longevity of the structure are tested via numerical simulations and dynamical models compared with observed features. The symmetry and sharpness of the ring, along with wave-like or expanding structures, serve as indicators of specific formation scenarios. Collisionally formed rings often display expanding waves or asymmetric features that fade over time, while stable, unchanging rings align with gradual accretion or internal processes. All these observational strategies serve as probes into Hoag's object's past. Examining multi-spectrum images, kinematic data, dark matter distribution, stellar ages, the environmental context, and gas dynamics enables astronomers to eliminate some theories and support others. Each clue adds to the cosmic detective story, refining our understanding of how the galaxy formed. The combined data help determine whether its ring resulted from a collision, steady accretion, dark matter effects, or internal evolution. These tests will clarify whether Hoag's object is a product of external interactions or internal development, shedding light on the mechanisms behind its remarkable symmetry. As more data are gathered, models are challenged and refined, each observation whispering clues about its history. This meticulous process aims to uncover how such an extraordinary object formed, challenging current astrophysical theories. Every measurement, image, and analysis brings us closer to understanding a galaxy that defies simple classification, pushing the limits of our knowledge. The pursuit of these observations is essential to unraveling the mysteries of Hoag's object. It inspires exploration of the universe's grand, intricate architecture with renewed curiosity. By probing its structure, motion, dark matter content, stellar populations, environment, and gas makeup, astronomers piece together its past, ruling out some scenarios while supporting others. The assembly of evidence reveals whether the galaxy's peculiar ring is a transient feature or a stable structure, formed by external forces or internal mechanisms. Ultimately, these observational tests aim to determine whether Hoag's object originated from a collision, gradual accretion, dark matter effects, or internal dynamical evolution. Clarifying its origins enhances our understanding of galaxy formation and cosmic evolution. As new data emerge, models can be adjusted, leading to a more complete picture of this extraordinary galaxy. Its unique form acts as a natural laboratory for testing theories of galaxy dynamics, evolution, and the influence of dark matter on large-scale structures. In some, combining multi-wavelength imaging, kinematic analysis, dark matter modeling, stellar population studies, environmental assessments, and gas content evaluation forms a comprehensive approach. This multifaceted strategy enables astronomers to decode Hoag's object's history, distinguish among competing models, and reveal the processes shaping such galaxies. Each observational effort contributes crucial pieces, ultimately helping us understand enigmatic objects that challenge our notions of galaxy formation. The quest to understand Hoag's object exemplifies the scientific process, an ongoing pursuit driven by careful observation, analysis, and refinement. It reminds us of the complex interplay of forces shaping the universe and underscores the importance of detailed, multidisciplinary strategies. Through these efforts, we deepen our grasp of cosmic structure, the role of dark matter, and the diverse pathways galaxies can take, inspired by the striking symmetry and mystery of this exceptional galaxy. The answer isn't as straightforward as it might seem. When scientists first observed Hoag's object through powerful telescopes, it looked like a cosmic miracle, an almost perfect ring of luminous stars encircling a dense nucleus, resembling a small, bright galaxy. Its symmetry, clarity, and isolation suggested something extraordinary. But the question remains, does it obey the known laws of physics, or does it challenge our understanding? Fundamentally, yes. Hoag's object does obey the laws of physics. Its rotation follows the principles of Newtonian mechanics and Einstein's general relativity. The star's orbits around the galaxy's center match gravitational predictions based on its mass distribution. Its rotation curve, how velocity varies with distance from the core, can be modeled with current understanding of gravity and dark matter. In that sense, it's governed by the same physical rules as our solar system or the Milky Way. However, what makes Hoag's object perplexing isn't just its adherence to these laws, but how unexpectedly it does so. Galaxy formation theories suggest that galaxies form through the gravitational collapse of gas and dust, evolving via mergers, accretion, and dynamical interactions. Most galaxies are irregular, elongated, or asymmetrical. Hoag's object? It's a perfect ring, a shape that indicates stability and harmony, almost too pristine to result from conventional galactic evolution. This symmetry hints at some underlying physics working in concert to maintain such stability over cosmic timescales. It's analogous to a perfectly balanced spinning top governed by physics, yet its extraordinary symmetry makes it seem almost unnatural. How did such a structure form and persist without dispersing, merging, or evolving into a different shape? Some models propose dark matter plays a key role. Dark matter, an invisible substance comprising about 85% of the universe's matter, exerts gravity that influences galaxy structures. In Hoag's object, dark matter could provide the gravitational glue stabilizing the luminous ring, preventing dispersal or collapse. Its influence aligns with current understanding of dark matter's role in galaxy formation, but the peculiar, highly symmetrical placement and pristine ring raise questions about whether dark matter's behavior here is fully understood. Other hypotheses involve collision events. Some scientists suggest Hoag's object could be the result of a specific galactic collision, a head-on encounter that flung out material into a ring. Typically, such collisions leave signs like tidal tails, distorted shapes, or star and gas streaks. But Hoag's object is remarkably undisturbed and symmetrical, making this scenario less convincing unless the collision happened at just the right angle, velocity, and timing. Even then, physics puzzles how such a fragile structure could survive long enough to be observed today. Internal processes are also considered. Waves propagating through the galaxy's gas might trigger star formation in a ring due to dynamical resonances or gravitational instabilities. These mechanisms are rooted in well-understood physics, like those governing spiral arms or ring structures in barred spirals. But Hoag's object isn't a typical spiral galaxy. Its perfect circularity and isolation suggest these internal processes might be at play in an unexpected way, possibly indicating new physics or subtle refinements to existing models. Its age adds another layer of mystery. The stars in the ring seem relatively young, glowing with the intense brightness of recent star formation, while the core appears older, denser, and more evolved. How does this gradient fit with physical laws? It suggests ongoing or episodic star formation in the ring, perhaps fueled by accumulated gas and dust, again implicating gravitational dynamics, gas physics, and magnetic fields, all within the framework of known physics. Yet the precision of these processes makes Hoag's object appear almost unreal. Every step toward understanding Hoag's object involves applying our current physical laws: gravity, thermodynamics, electromagnetism, nuclear physics. But its symmetry, stability, and isolation push these laws to their limits. They imply we might be missing key pieces, perhaps undiscovered physics like new dark matter properties or unknown stellar processes, or that the laws, when scaled up to cosmic proportions, can produce appearances that seem surreal. In many ways, Hoag's object functions as a cosmic mirror, reflecting what we know while exposing what remains unknown. It obeys the laws, absolutely, but also highlights how much more we need to learn about the universe's complex, strange, and beautiful structures. It's not a violation of physics, rather, it's an invitation to further exploration. It reminds us that the universe, in all its complexity, likely harbors secrets capable of challenging and refining the laws we've held for generations. Among the many mysteries surrounding Hoag's object, one of the most perplexing involves the peculiar gravitational effects observed within its structure. When astronomers peer into this cosmic jewel with our most sensitive instruments, what they find only deepens the enigma. The gravitational interactions in and around Hoag's object seem to defy expectations based on our understanding of more familiar galaxies. One of the earliest anomalies noted is the seemingly paradoxical distribution of mass within Hoag's object. Typically, in galaxies, mass, stars, gas, or dark matter is distributed proportionally, with visible matter tracing the gravitational well created mostly by dark matter. However, detailed gravitational lensing studies have revealed a discrepancy. The mass inferred from lensing appears concentrated differently than expected, not aligning well with the visible matter distribution. This suggests a significant amount of unseen mass, probably dark matter, but its configuration seems unusual. Instead of a sprawling halo, dark matter seems concentrated along the stable ring, or perhaps in an external halo shaping the galaxy's gravity. Such a distribution raises questions about how dark matter interacts with visible components, and whether the galaxy's formation history has led to an asymmetric dark matter halo, influencing gravitational dynamics in unexpected ways. Adding to this peculiarity are gravitational perturbations affecting the motion of stars within the ring. Stellar velocity measurements reveal that stars orbit with velocities that defy simple explanations. The velocities are high and arranged in a way indicating the ring isn't transient but a stable, self-sustaining feature. Yet the way stars move sometimes indicates subtle gravitational anomalies, regions where gravity appears stronger or weaker than expected from visible matter alone. In some cases, astronomers have noted gravitational tidal effects inconsistent with the galaxy's morphology. For example, stellar streams, ribbons of stars stretching along the ring, are observed in certain regions. These streams typically signal past gravitational interactions, yet Hoag's object shows no signs of recent collisions with other galaxies. Their presence hints at a history of gravitational disturbances or internal dynamical processes that mimic effects seen in more tumultuous galaxies. Further complicating matters are localized anomalies in gravitational potential. Mapping the gravitational field reveals that in certain regions, the potential fluctuates unexpectedly. These fluctuations are not easily explained by stars alone. Instead, they suggest hidden mass components, perhaps dark matter clumps or black holes yet to be detected. These areas are often associated with peculiar stellar motions, stars on highly elliptical orbits, or velocities changing unexpectedly over short distances. This indicates the presence of unseen influences shaping stellar dynamics. A particularly striking anomaly involves the core. The dense nucleus appears surprisingly stable and isolated, yet gravitational studies show it impacts the whole galaxy's gravity in unexpected ways. For example, some measurements indicate that the core's gravitational influence extends farther than expected, subtly warping the ring's shape, an effect comparable to a massive but invisible gravitational lens outside our line of sight. Such influence suggests an unseen mass exerting subtle forces on the galaxy's structure. Adding to the gravitational mysteries are indications that Hoag's object's rotation curve, the way stellar velocities change with radius, doesn't follow typical patterns seen in spiral galaxies. Usually, a rotation curve rises smoothly before flattening, driven by dark matter halos, but in Hoag's object, the velocities show irregularities. Some regions exhibit sharp rises with radius, then plateau unexpectedly or display localized dips. This irregularity hints at a complex internal gravitational landscape that standard models struggle to match, suggesting variable mass distributions or unusual dark matter configurations. The peculiar gravitational effects suggest Hoag's object might not conform to typical galaxy formation models. Its gravitational imprint hints at a dynamic past, perhaps involving gravitational disturbances from unseen masses or historical events leaving lasting imprints. These could include the accretion of intergalactic material, strange dark matter interactions, or exotic physics yet to be understood. As astronomers continue to explore Hoag's object with more sophisticated instruments, they are struck by its intricate gravitational signature, a dance of unseen forces, challenging and expanding our understanding of physics on cosmic scales. Each observation uncovers another layer of complexity, as if the galaxy itself is a cosmic Rorschach, reflecting our limited grasp of the universe's true nature. What remains clear is that Hoag's object, with its strange gravitational effects, is not just a simple ring, but a profound puzzle, a celestial enigma, urging scientists to peel back layers of darkness to understand the forces shaping such extraordinary structures. Could modified theories of gravity hold the key to understanding the bewildering structure of Hoag's object? It's a tantalizing question that pushes astronomers and physicists to think beyond the conventional confines of Einstein's general relativity. For decades, the prevailing framework has been that gravity, governed by Einstein's equations, shapes the universe's large-scale structures. But Hoag's object doesn't quite fit neatly into these models. Its perfect symmetry, stable ring, and isolated environment challenge the assumptions that guide our understanding of galaxy formation and evolution. General relativity has been a remarkably successful theory, fitting a vast array of observations, from the bending of light around massive objects to the intricate dance of planets and black holes. Yet, the universe itself continues to surprise us. Dark matter and dark energy, which together account for about 96% of the universe's total mass energy content, remain enigmatic. These unseen components are invoked to explain the rotation curves of galaxies, the accelerated expansion of the universe, and large-scale structure formations, puzzles that have led some scientists to question if our understanding of gravity at cosmic scales is complete. Enter modified theories of gravity, alternative frameworks attempting to tweak, extend, or replace Einstein's equations to better describe the universe's behavior without relying solely on dark matter or dark energy. Some of these theories propose additional fields or parameters that influence how gravity behaves over vast distances or in specific environments. For example, modified Newtonian dynamics, or MOND, suggests that Newton's laws need adjusting at extremely low acceleration levels, which are common in the outskirts of galaxies. Others, like FR gravity models, introduce functions of the Ricci scalar curvature to modify Einstein's equations, potentially altering the way gravity acts on large scales. Could such theories help explain Hoag's object's remarkable features? Well, considering its near-perfect circularity and the stability of its luminous ring, some scientists speculate that standard models might be missing crucial factors. If gravity operates differently at galactic or intergalactic distances than we currently believe, then the formation of a structure like Hoag's object might become more intuitive, almost inevitable, even in a universe governed by these alternative rules. Imagine a scenario where modified gravity causes matter to settle into stable, ring-like configurations more readily than in traditional models. Under normal gravity, the likelihood of such an extraordinary symmetrical ring forming and persisting over billions of years seems slim. But if gravity's behavior is altered at specific scales or densities, perhaps the conditions for such stability are naturally met. That could explain why Hoag's object exists in a universe that otherwise seems hostile to such delicate structures. Its formation might not have been a rare cosmic accident, but rather a natural consequence of physics operating differently than we've assumed. Furthermore, the isolated nature of Hoag's object could lend support to these ideas. Isolated galaxies tend to lack the gravitational perturbations that might distort or disrupt more typical spiral or elliptical galaxies. If modified gravity can account for the stability and symmetry of such galaxies without needing artificial fine-tuning or unlikely past interactions, then perhaps this framework deserves serious consideration. It might reveal that the universe's laws are more flexible than previously thought, accommodating new configurations and structures. On the other hand, these theories are not without challenges. Modified gravity models often face difficulty reconciling with observations across multiple scales, from the precise orbit of planets to the large-scale clustering of galaxies. While they might elegantly explain some features of Hoag's object, they must also fit a panoply of other cosmic phenomena. Matching the detailed cosmic microwave background patterns, galaxy rotation curves, gravitational lensing, and large-scale structure formation all at once is a demanding puzzle. Yet Hoag's object stands as a luminous beacon, literally and figuratively, highlighting gaps in our current understanding. It invites us to think outside the box, to entertain the possibility that the cosmos might be governed by laws subtly different at extraordinary scales or under unique circumstances. If modified gravity theories can be fine-tuned to explain the galaxy's captivating symmetry and stability, they could revolutionize our grasp of the universe, offering insights into the fundamental nature of reality. Ultimately, whether these theories will prove the answer or merely deepen the mystery remains to be seen. But in the dance of light shimmering around Hoag's object, there's a whisper of something more, a hint that our universe might be far more complex, strange, and beautiful than our current theories can fully describe. It's a cosmic enigma that compels us to continuously question, and perhaps one day to unlock the profound secrets woven into the very fabric of space-time itself. The dynamics of Hoag's object challenge our understanding of gravity, questioning long-held models of cosmic motion and matter distribution. Unlike most galaxies, whose stellar motion aligns with established gravitational physics, stars within Hoag's object's luminous ring defy expectations, prompting us to reconsider fundamental forces in the universe. Typical spiral and elliptical galaxies exhibit predictable patterns. Stars orbit the galaxy's center at velocities related to the enclosed mass. Newtonian gravity and Einstein's general relativity suggest that faster stars imply more mass within their orbit. Rotation curves, plots of velocity versus radius, often flatten at large distances due to dark matter halos, which exert additional gravity, preventing stars from drifting away at high velocities. Dark matter's presence explains these flat rotation curves and supports the idea of a universe filled with unseen mass. Hoag's object, however, defies this framework. Its luminous, symmetric ring features stars moving at high, uniform velocities that suggest more mass than visible matter accounts for. Applying standard models reveals a stark discrepancy. The calculated total mass needed to sustain these velocities demands unseen material in quantities incompatible with the galaxy's calm, symmetric appearance. Its stars maintain consistent velocities across various radii, unlike typical galaxies that exhibit a flattening of the rotation curve. This indicates a gravitational environment that diverges from standard expectations, raising questions about the distribution and nature of dark matter in this galaxy. The galaxy's rotation curve not only challenges dark matter models, but also invites alternative theories like modified Newtonian dynamics, MOND. MOND proposes that gravity behaves differently at low accelerations, reducing the need for dark matter. However, Hoag's object's stability and orderly structure impose strict constraints. Its symmetry and calm appearance seem at odds with predictions from modified gravity models, which often involve turbulence or anomalies. Its well-preserved ring and stable stellar motions suggest complexities that are difficult to reconcile with such alternatives, hinting at gaps in these theories. The shape and longevity of Hoag's object imply a finely balanced gravitational state. Its pristine ring-like form points to a unique formation history, perhaps from a gentle accretion of gas or a near-miss collision that resulted in a symmetrical ring. Such scenarios typically produce distortions, warps, or irregularities, yet this galaxy remains remarkably calm and undisturbed. The absence of signs of recent interactions questions how its delicate structure maintained coherence over cosmic time, deepening the mystery. This presents a significant challenge to models of galaxy formation and the distribution of matter in the universe. Our current theories may overlook unseen physics or exotic particles operating on galactic or cosmological scales. Could there be a form of dark matter, perhaps composed of unusual particles, that arranges itself in a way to produce such symmetry and stability? Might modified gravity, involving new fields or particles, better explain the observed dynamics? These questions suggest that the current understanding of the universe is incomplete. Some hypotheses explore that gravity might not be entirely universal, possibly varying under specific conditions or scales. Theories proposing variable gravity could reconcile Hoag's object's behavior with larger cosmological models. Although these ideas are speculative, they highlight the possibility that unseen forces or unconventional matter distributions influence galactic dynamics more profoundly than currently understood. No existing model fully accounts for the galaxy's perfect symmetry combined with its unusual stellar velocities, illustrating a significant gap in our knowledge. Hoag's object underscores that our grasp of gravity, dark matter, and galaxy formation remains limited. Its unique properties make it an astrophysical laboratory, a natural anomaly urging us to refine existing theories or develop new physics. The galaxy raises fundamental questions. Is gravity different at cosmic scales? Is matter distributed in ways yet undetectable? Could unknown forces or particles be shaping galactic behavior? These questions highlight that our understanding of physical laws on cosmic scales may be incomplete. The galaxy's stability and symmetry suggest a finely tuned gravitational equilibrium. Its unusual formation might have involved interactions or processes not yet understood. Perhaps a gentle accretion or a rare event created its ring. However, such pristine symmetry is uncommon, as galactic interactions typically generate distortions. Its calm and symmetric appearance challenges current theories, which struggle to explain its coherence over such a long period without disruption. Hoag's object acts as a cosmic enigma, a striking, elegant structure that resists simple explanation. Its stable, symmetric ring and peculiar stellar motions challenge the completeness of our gravitational theories. The galaxy suggests that our physical laws might operate differently at large scales, and that the universe still holds many secrets. Its existence reminds us that even the most beautiful structures can harbor profound mysteries about the forces shaping the cosmos. As an extraordinary astronomical phenomenon, Hoag's object pushes us to investigate the universe's underlying fabric. It prompts questions about whether gravity varies across contexts, whether matter is hidden in unexpected forms, or whether unknown forces are at play. Its peculiar dynamics reveal potential gaps in our understanding, indicating that our models of cosmic evolution, matter distribution, and gravitational physics need refinement. The galaxy's stability and unique features serve as a beacon, inspiring ongoing research and challenging the foundations of astrophysics. This galaxy exemplifies how the universe continually surprises us. Its unexpected properties underscore the importance of questioning established theories and seeking new physics. As we explore cosmic phenomena like Hoag's object, we recognize that our journey toward understanding the universe is far from complete, and that some aspects of nature's fundamental laws remain elusive, awaiting discovery. Hoag's object presents intriguing puzzles and paradoxes that challenge our understanding of physics and the universe. Its perfectly symmetrical ring surrounding a dense core appears almost surreal, raising fundamental questions about astrophysical laws. One major mystery is its stability. An object so delicately balanced has persisted for billions of years without dispersing or collapsing. The galaxy's luminous edge-on ring seems in a remarkably stable orbit. Normally, galactic collisions or interactions cause chaos. Stars shift orbits, structures distort. Yet, Hoag's object maintains pristine symmetry over cosmic time. What physics enables such an enduring, immaculate structure? Could unknown forces, possibly involving dark matter, hold it together in ways our models can't yet explain? Its formation also raises paradoxes. Standard galaxy theories suggest they form through gas and dark matter accretion or mergers, but Hoag's object defies these processes. Its nucleus is a dense elliptical core, likely housing older stars, while the ring contains young, bright stars, an age gap difficult to reconcile with a straightforward evolutionary history. How can such a stark disparity in stellar ages exist within a single isolated galaxy with perfect symmetry? Its isolation adds to the mystery. Most ring galaxies result from collisions or interactions, which leave telltale signs: distorted shapes, tidal tails, star streams. But Hoag's object is remarkably lonely, with no evident signs of recent encounters. How did its ring form? Perhaps internal processes like dark matter halo dynamics generated the ring through internal resonances or waves without external triggers. Alternatively, an internal event could have propelled gas into a ring, challenging conventional external formation models. Dark matter may play a role. Its unusual distribution around Hoag's object could produce gravitational effects that organize stars into a stable ring. If so, it suggests dark matter influences galaxy morphology in ways we don't fully understand. Such effects could point to new physics beyond current models. The situation presents a paradox. Could the elusive dark matter hint at fundamental physics beyond the standard paradigm? The dynamics within the ring further deepen the puzzles. How do stars orbit so coherently? Most galaxies show a range of stellar velocities and orbital inclinations, creating complex patterns. Yet Hoag's object stars seem to rotate uniformly, almost like a choreographed procession. This order defies expectations. Usually, differential rotation or perturbations generate chaos over time, but here, stars glide smoothly around the core. Are unknown stabilizing forces or resonances at work? Or is this a transient phase, a snapshot in the galaxy's evolution? Its brightness profile adds another paradox. The core is densely populated with older stars, while the ring glows with young, luminous stars. The origin of this gas and its subsequent formation into a perfect ring remains elusive. Did the galaxy accumulate gas from the intergalactic medium, or recycle stellar material? If gas accretion played a role, how did it settle into a ring without dispersing? Such questions challenge our understanding of gas dynamics and star formation in galaxies. Some models propose specific initial conditions, particular angular momentum distributions, that led to Hoag's object's formation. But these theories seem barely sufficient to explain its symmetry, suggesting it may be a rare cosmic accident, a pristine galaxy frozen in time, or that our models are incomplete. Its age, probably billions of years, raises the paradox of its longevity. How has such a delicate structure persisted amidst universal gravitational interactions? Does it imply stabilizing factors or self-regulating mechanisms we don't yet grasp? Or could it be in a transient stage, destined to evolve into a different form over cosmic timescales? All these puzzles imply Hoag's object might be more than a galaxy curiosity. It could be a window into new physics, revealing mechanisms governing galaxy morphology, star formation, and dark matter's role. It challenges existing paradigms about galaxy formation and evolution, urging scientists to reconsider fundamental laws of the universe. Continued study of this cosmic enigma may uncover new complexities, pushing the boundaries of our knowledge and exposing mysteries that remain forever beyond our reach. Hoag's object challenges conventional wisdom in astonishing ways, making it a cosmic puzzle that perplexes even seasoned astronomers. Imagine gazing at a galaxy that appears almost too perfect, like a jewel polished flawlessly, and realizing its very existence upsets our understanding of galaxy formation and behavior. That's what makes Hoag's object so intriguing. First, its extraordinary structure defies typical galaxy classifications. Most galaxies are spirals, ellipticals, or irregulars, chaotic, sprawling arrangements of stars, gas, and dust. But Hoag's object, it's a luminous, near-perfect ring with a dense core at the center, resembling a cosmic donut. What's baffling is the remarkable symmetry of this ring, as if painted with purpose. This symmetry isn't just visually pleasing, it defies expectations because gravitational forces tend to distort or reshape such structures over time. For a ring so perfect and stable to exist, it would need to be in fine-tuned balance, yet the universe rarely offers such fragile structures without hidden factors. Next, consider its isolation. Hoag's object sits apart from dense galaxy clusters, floating serenely in the cosmic ocean, untouched by gravitational tug-of-war typical of crowded regions. Normally, galaxies in clusters interact, collide, or merge, creating complex features. But Hoag's object appears to have remained untouched for billions of years, maintaining its pristine symmetry. How does a structure as delicate as a ring, where stars orbit precisely, avoid gravitational disturbances from neighbors? It's almost as if it was designed to exist alone, a cosmic masterpiece crafted in solitude. Moreover, the galaxy's stability defies common sense. Many structures in the universe are transient on cosmic timescales, expected to evolve, collide, or collapse. Yet Hoag's object has remained relatively unchanged for billions of years. Its ring continues to sparkle, its core remains dense, and symmetry persists, almost frozen in cosmic time. This persistent stability hints at unseen factors at work, perhaps halos of dark matter or exotic physics maintaining equilibrium. Ordinary physics suggests such a symmetric ring should dissipate or collapse, but it endures. Its formation further puzzles scientists. Conventional models don't readily explain how a perfect ring forms initially. Most ideas suggest rings form through galaxy collisions or gravitational influences from nearby galaxies, which cause gas and stars to pile into a ring. But Hoag's object shows no signs of recent interactions or nearby companions, no satellite galaxies or remnants indicating a recent collision. It's as if the ring formed spontaneously or through mechanisms beyond current understanding. A particularly remarkable aspect is how the ring persists without dispersing. Typically, stars drift apart or settle into stable configurations over time, yet Hoag's object exhibits a harmonious ring that seems to defy this tendency. What unseen force or physics holds the stars in perfect orbit? Could an unseen halo of dark matter be acting like gravitational glue, or might exotic physics beyond current theories be preventing the ring from dissipating? Its existence also prompts questions about dark matter and dark energy, which constitute much of the universe's mass energy. Some scientists propose that a massive halo of dark matter surrounds the galaxy, shaping star and gas dynamics in ways yet to be understood. Without this unseen component, the galaxy's stability and symmetry would be difficult to explain. The dark matter halo might serve as an invisible scaffold, preventing the ring from spreading or collapsing. Adding to the paradox is the brightness of the galaxy. The ring shines intensely with young, hot stars emitting bright light, contrasting with older, denser stars in the core. This patchwork of stellar ages raises questions about how star formation continues in such an isolated environment. Was something triggered to start star birth in the ring? Was it spontaneous or caused by an unseen event? The brightness and symmetry suggest finely tuned processes, another indication that Hoag's object defies typical models. The question arises, is Hoag's object unique or part of a larger hidden population? Could other galaxies have similar perfect, isolated structures, hidden by distance or current technology? If so, what does that imply about galaxy formation? Is the universe more capable of producing these rare structures than previously thought? Or is Hoag's object a fleeting anomaly, a cosmic masterpiece that exists against all odds? All these elements, its symmetry, stability, mysterious formation, and ambiguous origins, make Hoag's object a universe that refuses to conform. It highlights how much remains to be understood about the cosmos, how nature surprises us with designs and behaviors that challenge logic. Sometimes the universe operates on principles that only begin to reveal themselves, slipping through the cracks of current knowledge. Could unseen influences, forces, particles, or laws be at play? What we do not yet comprehend makes this galaxy compelling. Its existence is a question mark in our cosmic narrative, urging scientists to look deeper, think broader, and embrace the universe's complexity. It's not just a galaxy, it's a challenge to our understanding of nature's rules, a reminder that the most beautiful, symmetric structures can be the most perplexing, daring us to unlock their secrets. Hoag's object exemplifies the thrill of cosmic discovery, a testament to how much there is still to learn. Its intricate layers threaten to redefine what we think we know about the universe. Unseen influences, unknown forces or particles, may be shaping it, inviting curiosity and exploration. This galaxy's existence defies expectations, highlighting that the universe's most elegant structures often hold the deepest mysteries waiting for us to uncover. Imagine the universe as a grand cosmic artist, crafting galaxies over billions of years, each with its own story woven from gravity, gas, stars, and dark matter. Typically, galaxies follow certain patterns: spiral arms gracefully winding outward, elliptical formations that are more rounded and less structured, irregular shapes that seem chaotic but are still governed by fundamental forces. But Hoag's object is like an artist who threw away the rulebook, presenting a shape so peculiar it challenges what astronomers know about galaxy formation. The most striking feature of Hoag's object is its perfectly circular ring of bright, young stars surrounding a dense, spheroidal core. Such symmetry is rare. Most galaxies exhibit distortion, asymmetry, or irregularity, especially over billions of years, when interactions, collisions, or gravitational disturbances tend to warp structures. Yet, Hoag's object maintains immaculate symmetry. Its ring is so well defined and uniform it resembles a cosmic jewel, a ring nestled around a nucleus. This raises an immediate contradiction. How could such a delicate, perfectly formed ring remain stable over cosmic timescales, especially when gravitational interactions and internal dynamics tend to disrupt such structures? In standard models, rings like this are often transient features, residues of collisions or density waves caused by interactions with neighboring galaxies. But Hoag's object sits in splendid isolation, far from other massive galaxies, with no signs of recent collisions or disturbances. It is almost as if it was born with this perfect ring, defying expectations that such symmetry is fragile and easily broken. Its isolation offers no clues of cosmic violence needed to sculpt such a structure, prompting reconsideration of how these formations can form and persist without external catalysts. Then, there's the matter of its size and mass distribution. The luminous ring is composed of young, hot stars, bright and blue, indicating recent or ongoing star formation. Conversely, the core is densely packed with older, redder stars, creating a stark contrast that hints at different histories and compositions. This division is perplexing compared to typical galaxies, where stars of various ages are often intermingled. In spirals, star formation occurs along the arms, while in elliptical galaxies, stars tend to be older and more uniformly dispersed. The neatly separated concentric layers in Hoag's object seem almost artificially arranged, raising questions about how such stratification was established. Its rotation dynamics also pose a paradox. Observations suggest that the galaxy rotates so that the ring and core could be dynamically independent components, yet they coexist stably. Usually, the gravitational pull of the center influences surrounding stars and gas, leading to warps or spiral arms. But here, the ring seems almost detached in terms of dynamics, rotating as a coherent structure without expected gravitational chaos. Does this imply unseen forces or halos of dark matter sculpting its shape? Or does it suggest traditional gravitational models fall short in explaining such rare structures? Adding to the mystery is the galaxy's age and longevity. Hoag's features imply a long, stable existence. Yet in many galaxies, rings and similar structures dissociate over time, or are restructured by external forces. Its stability hints at an unusual internal or external mechanism preventing disintegration. Could some exotic physics be involved? A hidden force or peculiar dark matter distribution acting as a cosmic scaffold? Or does it challenge the idea that galaxy shapes are primarily formed through collisions and gravity, perhaps instead arising from subtle, mysterious processes? The chemical composition further complicates understanding. The core contains older, metal-rich stars typical of mature centers. The ring, however, is filled with relatively young, metal-poor stars formed in a burst of star formation. In typical galaxy evolution, such a sharp dichotomy suggests interactions or accretion events. But evidence of recent mergers or gas inflows is lacking, raising the question, can a galaxy internally generate such a neat, star-forming ring without external influence? If so, what processes would produce it? Hoag's object is a stable, isolated entity, unlike the turbulent, collision-heavy environments seen elsewhere. Most galaxies evolve through mergers, accretions, tidal forces that distort them. Hoag's object appears to avoid this chaos, maintaining its peculiar shape over billions of years. This raises whether we are witnessing a rare or fleeting phase in galactic evolution, or if it's a stable, long-lived anomaly forcing us to reconsider canonical pathways of galaxy formation. All these features, its symmetry, isolation, stellar populations, dynamic stability, and luminous ring, stand in stark contrast to expectations from common galaxy observations. Instead of the chaotic aftermath of collisions or a gradual spiral development, Hoag's object seems to have formed through a different set of circumstances, hinting there are hidden laws or pathways yet to be understood. It challenges the notion that galaxy shapes are primarily dictated by violent interactions, suggesting subtle or exotic physics may be involved. Its existence broadens our theories and implies galaxy formation is more diverse and mysterious than current models suggest. Hoag's object isn't just a beautiful anomaly. It might be a key to unlocking new understanding about the universe's fundamental mechanics and galaxy evolution. Its peculiar features invite questions about how galaxies can remain so symmetric and stable long-term, especially in isolation. Its unusual properties prompt reconsideration of assumptions that galaxy formation depends mainly on collisions and gravitational disturbances, perhaps mechanisms driven by internal processes or unknown physics. This galaxy's presence shows that the universe's story of galaxy formation may include pathways we have yet to fully explore, revealing complexity beyond current understanding. Hoag's object presents profound logical challenges that make astronomers rethink many assumptions about the universe. Its existence defies typical galaxy formation and stability expectations, challenging traditional models and urging scientists to think outside the box. The symmetry of Hoag's object is especially baffling. It features a perfectly circular, luminous ring of stars encircling a dense core, with the entire structure symmetrical from our vantage point, a visual marvel that seems almost too perfect to be natural. Most galaxies form through chaotic interactions, mergers, and gravitational dances, resulting in irregular, warped, or extended shapes. Such flawless concentricity and symmetry are rare without disturbance or recovery mechanisms. How can a pristine ring remain stable over billions of years? This questions our understanding of gravitational dynamics and stellar stability. Shouldn't gravitational forces gradually distort or disperse such structures? Yet, Hoag's object appears to have maintained its elegant form for cosmic timescales, prompting questions about unseen forces or physical laws that might preserve its shape. Another puzzle concerns its formation. Conventional models suggest rings form from galactic interactions, collisions or gravitational perturbations that redistribute gas and stars. But Hoag's object is isolated, with no signs of recent interactions or neighboring galaxies triggering formation. Its environment is unusually quiet, almost as if it developed in a cosmic vacuum. This raises a conundrum. How did such a luminous, tidy ring form without external influences? If interactions are unlikely, then what internal processes could have led to its birth? Could it be due to some internal dynamical mechanism or an unusual phase of galaxy evolution unseen elsewhere? The absence of nearby companions hampers understanding, challenging existing astrophysical theories. The stability of Hoag's object over cosmic time is equally perplexing. Most universal structures are transient or evolve over millions or billions of years, often due to gravitational disturbance or internal dynamics. Hoag's object, however, appears remarkably stable, frozen in time like a cosmic sculpture. This stability suggests an unknown balancing act at work. Perhaps dark matter plays a role in maintaining its symmetry, or exotic physics involving unseen forces or particles counteracts collapses or dispersal. These ideas stretch current understanding and push us to consider physics operating at galactic scales beyond the known. Understanding the internal dynamics within the ring adds further mystery. How do stars orbit so peacefully? In more chaotic galaxies, stellar motions are turbulent. Stars collide, scatter, or stream along complex paths. Here, stars follow orderly, circular orbits aligned with the ring. What preserves this order? Might a hidden structure, like a dark matter disk, influence stellar motions? Or does the ring's stability stem from initial conditions at formation? The lack of clear evidence makes developing a comprehensive explanation difficult, making Hoag's object a cryptic piece in galaxy dynamics. The origin of Hoag's object remains perhaps the greatest challenge. How did such an extraordinary structure come into being? Standard galaxy formation models struggle to account for a perfect ring. Minor accretions or gentle gas infall seem insufficient to produce or sustain such symmetry. Could it be a rare cosmic anomaly? A one-in-a-billion accident? Or does it reveal a fundamental gap in understanding galaxy evolution? These questions force us to reconsider assumptions about the processes guiding galaxy formation and stability. Unseen influences further complicate the picture. Dark matter might be essential, acting as an invisible scaffold holding the galaxy together. If dark matter concentrates to support this structure, it raises questions about its properties and distribution. Understanding dark matter's role in formations like Hoag's object could reshape our views on its nature. Since dark matter interacts gravitationally but not electromagnetically, its configuration is inferred indirectly, making this a significant logical challenge. Speculations about exotic physics add another layer. Modifications to gravity or undiscovered particles might be influencing large-scale structures like Hoag's object. If true, such theories could overturn fundamental physics principles. The galaxy might be more than an oddity. It could offer insights into new physics realms that challenge the universe's laws. Explaining Hoag's object thus becomes a puzzle of physics as well as astronomy. Its isolation also raises questions. Being remote minimizes external influences, allowing internal physics to shape its structure. But this makes detection of forces or causes behind its formation harder, as there are no interactions or mergers. The formation must have been driven solely by internal processes, which are poorly understood. How internal mechanisms could produce and sustain such a perfect ring over billions of years stretches current models and understanding. Ultimately, Hoag's object pushes the boundaries of logical reasoning in astronomy. It encounters phenomena that don't fit into existing theories, inspiring new ideas, physics, and models. It reminds us the universe is an endless frontier of surprises, where beautiful structures can also be perplexing puzzles. It beckons astronomers to uncover deeper truths about cosmic origins, laws, and mysteries. Its perfect symmetry, stability, and isolated nature challenge assumptions, provoke new hypotheses, and serve as a cosmic beacon illuminating gaps in our understanding of galaxy formation, dark matter, and fundamental physics. Could Hoag's object be a rare exception, a cosmic fluke born from a chance alignment or unusual circumstances? Or might it be compelling evidence that our universe hides secrets we have yet to uncover? Unknown processes challenging our understanding of astrophysics? These questions have haunted astronomers and theorists alike, each observation prompting us to reconsider what we believe about galaxy formation and stability. Some skeptics argue Hoag's object might be a cosmic coincidence, an unusual galaxy resulting from rare astrophysical events that just happen to be observable from our vantage point. This perspective suggests it's an outlier, not requiring new physics to explain. Yet as we compare it to other galaxies, its perfect symmetry and isolation seem less like coincidence and more like a clue that something deeper is involved. Could it be a remnant of a cosmic past shaped by specific events? Perhaps it originated from collisions or interactions of smaller galaxies, leading to its pristine ring structure. But then, why does the ring remain so stable and intact over hundreds of millions of years? Most galaxy collisions produce chaotic or distorted remnants, yet Hoag's object's ring is smooth and perfectly centered around its core, almost like a piece of cosmic jewelry crafted in a single moment or sustained by unknown forces. Some propose dark matter plays a role in its formation and stability, acting as an invisible scaffold holding it together. Dark matter could have influenced its evolution in ways current models can't fully explain, sculpting the ring or maintaining its stability. Still, the nature and properties of dark matter remain elusive, among the biggest mysteries in modern physics. Could dark matter behave in ways that enable such structures? Or is an entirely different, unknown form of matter or energy involved? Others entertain the idea that Hoag's object hints at exotic physics or undiscovered cosmological phenomena. Might there be unknown forces, beyond gravity, electromagnetism, or nuclear interactions, that stabilize this elegant ring? Could a yet undetected interaction be responsible for its formation and persistence? These ideas are provocative because they suggest the universe may be more diverse and complex than our current theories permit. Ultimately, Hoag's object may not just be an outlier to explain away, but a window into uncharted processes or physics. It stands as a cosmic masterpiece that prompts us to question the limits of our knowledge and consider that our current models may be incomplete, missing vital components or principles that could revolutionize our understanding of the universe. Reflecting on Hoag's object, we recognize that the cosmos is a vast, mysterious realm, full of surprises that challenge both our knowledge and our imagination. Whether it's a rare exception or a signpost to new physics, it inspires us to look deeper, think broader, and maintain humility before the universe's enigmas. It highlights how much remains to be discovered, a glowing beacon urging exploration into the unknown, pushing the boundaries of what we understand about our universe and our place within it. Hoag's object stands as a stark reminder that despite our decades of studying the cosmos, there are still phenomena that elude complete understanding. It pushes the boundaries of what we think is possible within the framework of known physics and challenges the assumptions built into our models of galaxy formation and evolution. Most galaxies reveal a chaotic history of mergers, accretion, and gravitational interactions, creating structures that mirror their tumultuous pasts. Yet here is Hoag's object, so perfectly symmetrical, so eerily stable, that it feels almost like a cosmic sculpture, frozen in time. Its pristine ring, shining with young blue stars, encircles a dense yellow core, giving off an impression of meticulous design rather than the chaotic processes we usually associate with galactic evolution. This symmetry hints at stability, but stability in such an isolated, pristine form raises unsettling questions. How did such an elegant structure emerge without the violent interactions or mergers that traditionally sculpt galaxies? Our current theories about spiral or elliptical galaxies fall short in explaining Hoag's object's perfect symmetry. Usually, rings of stars form from specific events, collisions, resonances, or accretion of external material. Yet Hoag's does not seem to have undergone recent disruptive interactions. Its diffuse ring appears almost untouched by the chaos that longs to mark the universe's history. This suggests that our models miss some fundamental process, some unseen mechanism that either prevents distortion or actively preserves this form over billions of years. The galaxy's remarkable stability nudges us to question the role of dark matter in its structure. Dark matter is believed to make up most of the universe's mass, shaping the formation and behavior of galaxies. But can dark matter alone explain Hoag's object's perfect symmetry? Or might there be other, more exotic forces at play? Researchers have pondered whether invisible filaments of dark matter might act as scaffolding, holding the galaxy in its unusual configuration. Or perhaps, the galaxy is a rare cosmic coincidence, a fleeting snapshot in a rare stage of galactic life that challenges our ability to model cosmic evolution accurately. Another dimension of mystery surrounds the galaxy's formation. Traditional models suggest that galactic rings form through interactions with other galaxies or the accretion of interstellar gas, but Hoag's object appears isolated, with no signs of recent mergers or gravitational tug-of-wars. This isolation hints that some unknown process, possibly a slow, internal, dynamical evolution, created its ring, or that a yet undiscovered physical principle is at work. These puzzles reveal how little we know about the universe's true complexity. Hoag's object not only challenges our current models, but also inspires a humbling realization. The cosmos is far more inventive than our theories suggest. It hums with phenomena that we might never fully comprehend with our current tools, our physics, and our imagination. Its silent, perfect symmetry screams that there are layers of cosmic truth yet to be uncovered. truths that may require new physics, new insights, and an open mind willing to accept that the universe's greatest wonders are still waiting to be understood. The galaxy teaches us that our understanding is a moving target, a map that expands as we voyage deeper into the cosmos, constantly revealing that the universe still holds secrets larger and more strange than all we have yet imagined. Hoag's object isn't just a mysterious cosmic jewel. It might hold the keys to understanding some of the universe's most profound secrets. To grasp its significance, imagine looking back in time, not in centuries or millennia, but across billions of years of cosmic evolution. This galaxy, with its perfect ring and dense core, challenges our notions of how galaxies form and change, inviting us to question the very story of the universe. At the heart of this inquiry lies a simple yet profound idea. What if Hoag's object is a cosmic relic, a snapshot capturing an era long gone in the grand timeline of the cosmos? Its sheer symmetry and stability suggest it's remarkably aged, but also surprisingly resilient. This hints at a formation process so ancient that it predates many of the more chaotic, collision-driven galaxies we observe today. In other words, Hoag's object could be a window into the distant past, a relic that preserves conditions from an era when the universe was younger and less structured. One of the biggest mysteries surrounding Hoag's object is how it came to be. Conventional galaxy formation models often involve dramatic events, collisions, mergers, and the swirling chaos of cosmic interactions. Yet, this galaxy's perfect ring and its quiet stability seem to contradict those expectations. Could it be that Hoag's object formed in a more tranquil universe, from a slow, gentle accumulation of gas and stars? Or perhaps it was born from a rare, monumental collision that somehow left behind this elegant ring, like ripples spreading across a still pond. In pondering this, we realize that studying Hoag's object can shed light on dark matter's role in cosmic evolution. Dark matter, the elusive substance making up most of the universe's mass, influences how galaxies form and cluster. Its invisible presence binds galaxies together and guides their growth. The way Hoag's object maintains its shape and structure might reveal how dark matter interacts at large scales and whether it plays a role in preserving such pristine formations over billions of years. Additionally, the galaxy's unique structure might provide clues about matter distribution over cosmic time. The stellar populations within Hoag's object, stars of varying ages and compositions, serve as a cosmic archaeological record. By analyzing their properties, astronomers can trace back the sequence of events that led to the galaxy's current form. Did the galaxy form all at once, or did it grow gradually, with new stars forming in the ring from swirling gas? These questions help map the universe's timeline, when matter coalesced, how structures evolved, and how long it took galaxies like Hoag's object to reach their elegant maturity. The galaxy's isolation further amplifies its potential to inform us about the universe's evolution. Unlike galaxies in crowded clusters, Hoag's object exists somewhat alone, far from gravitational influences that could distort its form. This peaceful solitude provides a pristine environment in which to study fundamental processes, how galaxies grow and evolve without external interference. It's almost like conducting a controlled experiment in space, where the absence of nearby galaxies reveals the physics driving cosmic architecture. Studying Hoag's object could also help answer questions about cosmic acceleration and dark energy. These phenomena influence how the universe expands, and understanding how structures like this galaxy form and persist might offer indirect clues. If certain features of Hoag's object defy standard models, perhaps they hint at new physics or modifications to our current theories about gravity and cosmic expansion. Another tantalizing possibility is that Hoag's object might be a stepping stone to discovering exotic physics. The galaxy's unexpected stability, symmetry, and morphology could point toward phenomena beyond our current understanding. Perhaps unknown particles, new states of matter, or unconventional gravitational effects. Its existence challenges scientists to think beyond the standard models of cosmology, pushing the boundaries of what we believe about the universe's fundamental laws. Looking further ahead, Hoag's object might help refine models of galaxy formation over cosmic epochs. It acts as a cosmic puzzle piece, fitting into the broader picture of how the universe transitioned from a hot, dense plasma to today's vast, structured cosmos. Comparing this galaxy to others at different redshifts, that is, at different distances and cosmic times, can help piece together the evolutionary pathways of galaxies across billions of years. Moreover, understanding galaxies like Hoag's object helps unravel how the universe achieves its remarkable diversity. From sprawling spirals and barred galaxies to ellipticals and peculiar formations, each tells a story of cosmic history. Hoag's object, with its near-perfect ring, adds a chapter filled with rarity and elegance, suggesting that the universe's evolution isn't a straightforward march, but a complex dance influenced by initial conditions, dark matter halos, energetic feedback from stars and black holes, and perhaps even unknown influences. As scientists work to decipher its properties, they get closer to answering whether such galaxies arise naturally or if they hint at extraordinary, maybe quantum phenomena at galactic scales. Could this galaxy be a natural outcome of the universe's early symmetry? Or does it represent an anomaly, a cosmic exception that defies current models? The answers could revolutionize our understanding of the universe's history and future. Finally, studies of Hoag's object influence our perceptions of cosmic destiny. By understanding its stability and longevity, we gain insights into how the universe's large-scale structure persists over unfathomable spans of time. Do perfect rings endure billions of years, or are they transient, evolving into more complex forms as cosmic conditions change? These questions are central to grasping not only where the universe has been, but where it is headed. In contemplating Hoag's object, we peel back layers of cosmic history, revealing the interplay of gravity, dark matter, gas, and stars that crafted today's universe. It's a beacon calling us to question, explore, and understand the fundamental laws governing everything, from the tiniest particles to the grandest galaxies. Every detail of this galaxy, its shape, composition, and stability, is a clue, a narrative woven into the story of cosmic creation and evolution. As we decipher that story, Hoag's object reminds us that the universe still holds mysteries beyond our current grasp, beckoning us onward in our quest for knowledge. The mysteries surrounding Hoag's object challenge our understanding, hinting at phenomena and forces beyond our current knowledge. When astronomers first observed this mesmerizing galaxy, they expected familiar patterns rooted in well-understood physics and cosmic history. Instead, they encountered a puzzle, one suggesting forces that we have yet to fully grasp or even imagine. Take, for example, the galaxy's remarkably perfect ring, a structure so symmetrical and stable it seems sculpted rather than the result of chaotic cosmic events. Most galaxies form through tumultuous processes, collisions, mergers, accretion, and dark matter interactions. Yet Hoag's object stands apart, seemingly unaffected by such turmoil. Its ring isn't fragile, it's vibrant, well-maintained, orbiting a dense core with uncanny accuracy. Its stability over billions of years hints at unseen forces operating behind the scenes, maintaining cosmic harmony against the odds. Some scientists propose unknown fields or particles could influence the galaxy's behavior. Dark matter might not be a passive structure providing gravitational glue, but could interact with baryonic matter in ways that produce such a stable yet peculiar architecture. Unseen forces, constant, gentle but profound, might keep the ring in perfect orbit, resisting gravity's disruptive effects and internal instabilities. These forces may originate from physics beyond the standard model, hinting at undiscovered particles or force carriers influencing large-scale structure formation. The galaxy's rotation curves deepen the mystery. In typical spiral galaxies, stars in the outer regions orbit faster than expected, implying dark matter lurking in shadows. But in Hoag's object, star velocities suggest a delicate balance. This leads scientists to question, what if our laws of gravity are not entirely correct? Could modifications, like theories proposing extra dimensions or alternative forces, better explain its features? Might a fifth unknown force subtly guide stars, mimicking effects attributed to dark matter? Questions also arise about the formation of such an elegant structure. Traditional models suggest ring galaxies result from collisions or disturbances by nearby galaxies. Yet Hoag's object is isolated, seemingly untouched by surroundings. How then did this striking ring form? Some theories propose exotic physics, perhaps vortices in dark energy fields or cosmic string alignments, inducing a ring without collisions. These ideas stretch current cosmological understanding, hinting at forces shaping the universe in ways we haven't yet grasped. Within the galaxy's dense core, stars behave unexpectedly, Its stability over eons might imply influence from unknown gravitational or electromagnetic fields, or even new particles mediating interactions between stars and dark matter. If such phenomena exist, they would revolutionize physics, revealing forces operating on galactic scales yet hidden from laboratory detection. Adding to this intrigue is the galaxy's remarkable resistance to change. Most galaxies evolve via interactions, accretion, and internal dynamics. Hoag's object remains pristine, suggesting a cosmic balance, possibly a new force counteracting disruptive influences, maintaining symmetry and order. It might be an elegant feedback mechanism driven by unseen physics that preserves this galaxy's delicate architecture. Further, astronomers observe subtle anomalies in stellar motions. Some stars seem to move in ways defying simple gravitational models, hints that forces beyond gravity might be at work. Precise stellar orbits suggest a finely tuned environment, almost as if some hidden influence guides their paths, ensuring the ring's perfection. Could what we call dark matter be more than matter, perhaps a manifestation of new physics? Or could exotic fields or particles influence the universe's fabric? Scientists, using advanced telescopes and simulations, probe Hoag's object, but they face more questions than answers. Could the galaxy harbor undiscovered matter or energy, quietly orchestrating its stability? Might it be illuminated by forces that challenge universal constants? Could it be an anomaly, a sign that not all phenomena conform to current laws? The existence of Hoag's object hints at a universe richer and more complex than our models suggest. It implies unseen forces or phenomena underpin the cosmic dance. Rather than an oddity, it may serve as a signpost, guiding us toward new physics and deeper mysteries. Its perfect symmetry and stability raise questions about unknown forces, unseen phenomena, and the universe's true nature. It suggests realms of physics yet to be uncovered, forces operating on grand scales, influencing structures beyond current understanding. Exploring Hoag's object may reveal clues about the universe's fundamental makeup. It hints at phenomena that could reshape our understanding of physics and cosmology. Its existence challenges us to reconsider the laws governing matter, energy, and forces across the cosmos. Studying it more deeply might uncover new particles, fields, or principles, discoveries that could revolutionize our understanding of reality. The structure's perfect symmetry and apparent stability imply some unseen influence maintaining order, perhaps through mechanisms we haven't yet conceived. It could involve stable, exotic energy fields, interactions related to dark energy or forces beyond the four known fundamental interactions. These might be behind the formation, persistence, and resistance of the galaxy to cosmic evolution's natural perturbations. Moreover, the galaxy's peculiar stellar motions hint that forces beyond gravity are guiding star trajectories, subtle influences that help keep the ring intact. These might represent new physics, additional fields or particles shaping large-scale structures in ways we still don't fully comprehend. In sum, Hoag's object poses profound questions. Does it hint at unknown phenomena or forces? Is it governed by mysteries beyond our current models? Forces that could revolutionize physics? Its existence compels cosmologists to explore realms where unseen influences shape cosmic architecture. It may be a cosmic signpost, pointing toward a universe that is more wondrous and mysterious, packed with hidden forces and phenomena waiting to be discovered. Hoag's object stands out as a remarkable exception among the vast diversity of galaxies in our universe. When considering galaxy types, spiral, elliptical, irregular, lenticular, and this peculiar ring galaxy, the variety highlights how cosmic evolution can follow different paths through gravity, dark matter, and cosmic timing. In the cosmic universe, Hoag's object doesn't just seem to fit into existing categories. It challenges our classification schemes and prompts us to reconsider our galactic taxonomy. Most galaxies follow patterns shaped by their formation history and environment. Spiral galaxies, with their winding arms teeming with young stars, reflect ongoing star formation fueled by gas and dust. Ellipticals often result from mergers, their smooth profiles hinting at turbulent pasts with chaos and collision. Irregular galaxies appear as cosmic wildcards, disrupted by interactions or encounters, with fractured and asymmetric shapes. Hoag's object, however, defies these conventions. Its near-perfect luminous ring encircles a dense core, almost sculpted by some divine hand rather than natural processes. The symmetry appears untouched by the chaos that influences other galaxies. It looks serene, yet beneath that calm lies a complex, enigmatic history that scientists are just beginning to understand. Unlike many galaxies shaped by gravitational interactions, Hoag's object exists in remarkable isolation. Its surroundings are sparse. No nearby galaxies seem to influence its structure. This solitude makes it more puzzling. How did such a perfect ring form without the turbulence and interactions typical of similar structures? Was it from a collision, with a smaller galaxy or gas cloud caught in the core's gravity, stretching into a ring? Or might it be due to some intrinsic stability in cosmic physics, perhaps involving dark matter in ways we don't yet understand? This anomaly expands the boundaries of galaxy evolution models. It reminds us that the universe doesn't always follow our rules. Some galaxies are shaped by violent mergers and chaotic accretion, while others emerge from gentle, subtle processes that challenge detection. Hoag's object pushes these boundaries, hinting at pathways in galactic formation that remain obscure or unexplored. In a broader context, Hoag's object invites us to question the universality of classification schemes. Could its ring be a transient phase, an ephemeral stage destined to evolve into more familiar galaxies? Or is it more likely a stable, long-lived structure that hints at unseen physics, such as dark matter influences favoring ring formation? Its stability over billions of years suggests resilience and equilibrium that are hard to explain with straightforward models. Moreover, Hoag's object exemplifies the diversity of galactic environments. Many galaxies are part of bustling clusters, shaped heavily by neighbors and gravitational dynamics. In contrast, this galaxy's isolation underscores that galaxies can evolve quite differently depending on their surroundings. Some undergo violent interactions, resulting in chaotic shapes or starbursts, while others, like Hoag's object, seemingly find a cosmic balance, remaining tranquil enough to maintain their structure over cosmic timescales. The presence of Hoag's object within the grand mosaic of galactic diversity is particularly fascinating because it could unlock new physics or alternative formation theories. Traditional models often consider ring galaxies as products of collisions or resonance phenomena within barred spirals. Hoag's object, with its pristine symmetry and apparent lack of disturbance, challenges these frameworks. It suggests the involvement of exotic dark matter halos or unknown gravitational effects that permit such a serene, stable structure. Its existence also raises questions about our understanding of star formation, gas dynamics, and cosmic evolution. Might there be other galaxies waiting to be discovered that resemble Hoag's object, or exist in even more unexpected niches? Could there be a whole category of resilient ring galaxies yet to be identified with more advanced telescopes? This possibility broadens our view of the universe as an even more diverse, complex cosmic zoo. The bigger picture emphasizes the importance of cosmic serendipity. The universe can produce rare configurations that persist for billions of years, challenging the idea that certain structures are fleeting or unstable. It reminds us that our models are approximations, not complete truths. The universe functions like a master craftsman's workshop, filled with both expected and extraordinary masterpieces. Ultimately, Hoag's object stands as a testament to our ongoing cosmic discovery journey. It broadens our perspective and pushes the boundaries of understanding about galaxy formation, evolution, and underlying physics. This galaxy is more than a curiosity. It is a window into the universe's complexity, a beacon for the mysteries yet to be unraveled. It exemplifies that surprises always await, especially in the most unlikely forms, reminding us that the universe never ceases to fascinate with its endless variety. Could Hoag's object influence our models of cosmic development? Absolutely. It's a cosmic puzzle piece that might force astronomers and physicists to reconsider long-held assumptions about how galaxies form and evolve. This galaxy, with its nearly perfect ring encircling a dense core, might serve as a natural laboratory, an unanticipated example that challenges the standard theories, pushing scientists to refine their understanding or even develop entirely new models. Traditionally, when scientists think about galaxy formation, several key processes come into play. Many galaxies grow through gradual accretion of gas and dark matter, merging with smaller galaxies, or undergoing violent collisions that reshape their structure. The gravitational interactions among stars, gas, dark matter, and energy all contribute to these processes, fitting into a framework that has been built over decades through observation and simulation. But Hoag's object seems to stand apart from these models. The symmetry of the ring, its nearly impeccable shape, and the galaxy's overall stability over billions of years suggest that some of these common processes might not fully explain its origins. It seems to have achieved a state that is remarkably stable, a cosmic ballet in perfect harmony. If galaxy collisions or internal dynamics were solely responsible, we might expect to see signs of disturbances, asymmetries, or other remnants of a violent past. Instead, Hoag's object appears relatively untouched by such upheavals, as if nature herself designed it to be a picture of cosmic perfection. This raises the possibility that we may need to revisit the significance of dark matter in galaxy formation. Dark matter, which makes up a significant portion of the universe's mass, influences the large-scale structure of the cosmos. Dark matter halos are thought to be the scaffolding upon which galaxies are built. Could it be that certain configurations of dark matter lead to stable, ring-shaped galaxies like Hoag's object? Or perhaps there are unknown physics at play, forces or particles that influence galaxy morphology in ways we have yet to comprehend. If Hoag's object's stability and shape are partly governed by unseen influences, unlocking those secrets could revolutionize our understanding of dark matter, or even lead us toward new physics beyond the current model. Additionally, its isolation raises intriguing questions. Most large galaxies are part of clusters or groups, interacting gravitationally and exchanging material with neighbors. Hoag's object, however, sits in splendid solitude, seemingly untouched by the tumult around it. This loneliness could have allowed it to follow an entirely different evolutionary path, a path that might not be fully captured by current models. It hints that in some regions of the universe, galaxy formation might persist under different rules, driven more by local conditions or exotic forces than by the interactions we observe elsewhere. Moreover, Hoag's object beckons us to consider alternative origins. Perhaps it was formed from a unique event or series of events, such as an unusual cold collision, internal gravitational instabilities, or even a rare cosmic coincidence. Each possibility nudges theorists to expand their conceptual frameworks and explore scenarios outside the conventional script. If future research confirms that such galaxies are more common, or that their formation involves mechanisms entirely different from those previously thought, our cosmic narrative could shift dramatically. We might come to see the universe not as a straightforward playground of predictable laws, but as a cosmos replete with surprises, where the rules occasionally bend, and new physics emerge from the shadows. In essence, Hoag's object isn't just a rare celestial spectacle, it's a catalyst for scientific evolution. It challenges us to look beyond the familiar, to question what we think we know about the universe's grand design, and to embrace the possibility that cosmic development might be more intricate, diverse, and mysterious than our current models suggest. Future observations have the potential to unlock the many secrets that Hoag's object still guards so jealously. The galaxy's peculiar structure and apparent stability suggest that unraveling its origins isn't just about peering deep into space. It's about peering into the very processes that shape our universe. One of the most promising avenues lies in high-resolution spectroscopy. By meticulously analyzing the light coming from the stars within both the central core and the surrounding ring, astronomers can map the movement of stars and gas with incredible precision. This detailed kinematic data could reveal subtle differences in velocities, shedding light on whether the ring formed through an ancient collision, a slow accretion process, or some other cosmic event. For instance, if the stars in the ring exhibit signs of recent formation or show distinct motion patterns compared to the core, it might hint at a more violent past, such as a merger or a cosmic collision. Conversely, a smooth, uniform movement could support theories of internal dynamical processes or dark matter influences, suggesting that gravity sculpted this galaxy in a manner we have yet to fully comprehend. High-resolution imaging across multiple wavelengths also plays a crucial role. By observing Hoag's object in infrared, ultraviolet, and radio wavelengths, scientists can chart the distribution of different types of stars, interstellar gas, and dust. Ultraviolet observations could reveal regions of ongoing or recent star formation at the edges of the ring, something that might be unexpected given its age. Infrared data might uncover hidden structures within the core, or faint stellar populations that elude visible light detection, helping to piece together a timeline of its development. Radio observations, especially with very long baseline interferometry, could illuminate the presence of neutral hydrogen or molecular clouds, fuel for potential future star formation, or reveal interactions with unseen dark matter concentrations. Another frontier involves gravitational lensing studies, where light from distant objects is bent around the galaxy's mass. If Hoag's object is sitting amidst an unseen halo of dark matter, precise lensing measurements could map its distribution in detail. Such data might illuminate whether dark matter played an unexpected role in its formation or stability, forging a connection between the galaxy's peculiar structure and the invisible mass that dominates cosmic architecture. Finally, advanced computer simulations guided by observational data are an integral part of future efforts. These simulations can recreate various formation scenarios, from collision remnants to internal dynamical processes, enabling scientists to compare model predictions with actual observations. This iterative process helps eliminate unlikely origins and refine the most plausible ones. Looking ahead, next-generation telescopes like the James Webb Space Telescope, the Extremely Large Telescope, and the Square Kilometre Array will provide unprecedented clarity and depth. Their observations will not only peel back the layers of Hoag's object's history, but might also rewrite what we understand about galaxy formation itself. If we're lucky, these cosmic detectives will finally decode the galaxy that defies our current physics, bringing us a step closer to understanding the true nature of our universe. Astronomers' ongoing exploration of the universe's mysteries has intensified the search for galaxies resembling Hoag's object. These unique galaxies challenge our understanding of galaxy formation and stability, prompting scientists to refine theories and develop new models. Finding similar structures isn't just about cataloging cosmic oddities. It could reveal fundamental laws of nature, insights into dark matter, and clues about exotic physics beyond current theories. Ongoing sky surveys have helped identify rare ring-shaped galaxies. The Sloan Digital Sky Survey, SDSS, for example, has mapped millions of celestial objects, uncovering many peculiar galaxies, some with prominent rings or unusual morphologies akin to Hoag's object. By analyzing this extensive dataset, astronomers identify candidates, especially those with nearly perfect rings surrounding bright cores. However, SDSS's resolution and wavelength coverage have limitations, particularly when it comes to detecting faint stellar populations or subtle features. Upcoming surveys promise to revolutionize this search. The Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, slated to begin full operations shortly, will image about 20 billion galaxies over 12 years with unprecedented depth, resolution, and cadence. Its capabilities will enable astronomers to detect faint, diffuse structures and intricate features previously unseen, broadening the catalogue of ring galaxies. The LSST's vast dataset will likely lead to more discoveries of extreme or unique ring galaxies, possibly even more striking than Hoag's object. Its deep imaging will reveal faint stellar streams or shells, hinting at past interactions or unconventional formation processes. The rapid survey cadence will also facilitate the detection of transient phenomena or dynamic features, providing clues about internal stability or episodic star formation. Infrared observations are crucial, especially for galaxies hidden behind dust or dominated by older red stars. The European Space Agency and NASA's Euclid mission, designed to probe dark energy, dark matter, and galaxy evolution, will map billions of galaxies in near-infrared wavelengths. Euclid's high-resolution imaging and spectroscopy will help identify less obvious ring-like structures and improve understanding of their stellar populations and mass distributions, including dark matter halos. Such data might reveal that Hoag-like galaxies are more common than previously thought, merely hidden from optical surveys. The Nancy Grace Roman Space Telescope, NASA's upcoming infrared observatory, offers further opportunities. Its wide-field, high-resolution imaging will complement Euclid's data and facilitate the discovery of rare galaxy types, potentially uncovering more Hoag's object analogues. Roman's spectroscopy will allow detailed analysis of stellar populations and gas dynamics within the rings, helping us understand their origins and how such elegant structures can persist. Radio telescopes like the Square Kilometre Array, SKA, will further expand understanding beyond visible light. By observing neutral hydrogen gas, often extending beyond the visible galaxy, SKA can reveal past interactions, accretion events, or resonant ring formation mechanisms not visible in stellar images. If galaxies similar to Hoag's object are formed through exotic processes involving dark and baryonic matter interplay, radio observations might be key to uncovering their origins. Combining data from LSST, Euclid, Roman, and SKA offers a multi-wavelength perspective, each providing unique insights into the stellar, gaseous, and dark matter components of these galaxies. Such comprehensive observations are vital for distinguishing formation scenarios, whether rings resulted from collisions, long-term resonances, or more exotic cosmological phenomena. Machine learning and advanced data analysis will play an increasingly vital role in managing the enormous datasets of upcoming surveys. Algorithms trained to recognize properties of known ring galaxies can efficiently identify new candidates and flag objects for follow-up. Automation is essential because the scale of upcoming data exceeds what individual astronomers could manually analyze. Looking further ahead, the James Webb Space Telescope, JWST, will focus on promising candidates identified in broad surveys. With unparalleled sensitivity, JWST will provide detailed imaging and spectroscopy of stellar populations, nuclei, and surroundings, revealing whether these galaxies share origins with Hoag's object or evolved differently. Such studies will deepen understanding of galaxy morphologies and formation mechanisms. Future large telescopes like the Extremely Large Telescope, ELT, and the 30-meter telescope, TMT, aim to achieve even higher resolution and sensitivity. They will resolve fine details in distant ring galaxies, potentially billions of light-years away, helping track how these structures appear and evolve across cosmic time. Finding Hoag-like galaxies at various stages of development will clarify whether they are rare relics or more common phenomena, with their rarity perhaps due to fleeting conditions. As data accumulates, astronomers are increasingly considering that ring galaxies may not be rare, but elusive, transient phases in galaxy evolution, or results of special events. Extensive current surveys and upcoming missions will expand our inventory, helping determine if Hoag's object is an anomaly or part of a larger family of galaxies. Citizen science projects such as Galaxy Zoo accelerate discovery by engaging volunteers in galaxy classification. Such efforts help identify rare structures more rapidly, enabling researchers to focus on promising candidates. Collaborative efforts like these are instrumental in revealing more celestial wonders similar to Hoag's object. Every new discovery influences galaxy evolution models, especially if more galaxies resemble Hoag's object, with properties deviating from traditional formation pathways. These findings might prompt scientists to reconsider assumptions about galaxy growth, merging, and stability over billions of years. Some of these structures could stem from unseen effects, unknown physics, dark matter interactions, or yet undiscovered cosmic phenomena. The future of this exploration is promising, with each survey, telescope, and analytical tool deepening understanding of the universe's complexity. New candidates increase the likelihood that what we see as rare or unique structures are part of a continuum, perhaps representing natural stages or rare outcomes of galaxy evolution. The goal isn't simply to catalogue rare objects, but to unravel fundamental laws of the universe. As astronomers analyze data from these advanced surveys, they may find that such ring galaxies are keys to understanding cosmic laws and structure formation. The ongoing and upcoming surveys are essential tools that will uncover whether Hoag's object is a cosmic fluke or a glimpse into a more intricate universe. The potential discoveries ahead promise to transform our understanding of galaxy formation, stability, and evolution. Every new candidate links to bigger questions about the universe's origins and how its galaxies develop over cosmic time. With each observation, the boundary between known and unknown shifts outward, revealing more about the universe's beauty, complexity, and the structures it can produce. These efforts, driven by technological innovation and scientific curiosity, will likely uncover many more galaxies like Hoag's object, enabling us to see whether such objects are rare exceptions or common fleeting phenomena. As datasets grow and analysis methods improve, the cosmic landscape will be increasingly clear, showing us the diversity and forces shaping galaxies across space and time. The discovery of additional ring galaxies will help clarify whether structures like Hoag's object result from unusual events, long-term resonances, or exotic processes involving dark matter or other physics. Each new detection will inform and challenge current theories, potentially leading to revolutionary insights into the universe's architecture. By combining data across multiple wavelengths, from radio to infrared to optical, we will gain comprehensive views of these galaxies' components, helping us understand their formation histories and inner mechanics. Multi-wavelength studies are essential for resolving debates about their origins, collision-induced rings, internal resonances, or cosmological effects. Ultimately, our growing knowledge base, driven by cutting-edge surveys and analytical tools, brings us closer to answering fundamental questions about galaxy diversity and evolution. If multiple galaxies similar to Hoag's object are found, they could redefine our understanding of galaxy stability and formation. They might be snapshots of rare phases or the products of extraordinary events, each revealing more about how structures survive and evolve in cosmic environments. The next decade will be crucial in expanding our galaxy census and unraveling the mysteries of these enigmatic objects. As new datasets flow, they will reveal whether Hoag's object is unique or part of a population, providing insights into galaxy formation and the physical processes that produce such elegant rings. This pursuit is also a step toward understanding the universe's broader story, its origins, mechanisms, and capacity for creating beauty in unexpected forms. The journey to discover more Hoag-like galaxies is about uncovering the laws and processes underlying all cosmic structures. Each step forward, be it from new surveys, advanced telescopes, or citizen science, brings us closer to understanding the universe's complexity and grace. The quest continues, full of anticipation, with the promise of new revelations about galaxy nature and the universe itself. Advanced telescopes and cutting-edge technology are set to revolutionize our understanding of enigmatic galaxies like Hoag's object. The future of astrophysics lies in the ability to observe deeper, clearer, and in more detail than ever before, opening new windows into the universe's most mysterious structures. One of the most significant advancements will come from telescopes with vastly improved resolution and sensitivity. Upcoming observatories, such as the James Webb Space Telescope, the Vera C. Rubin Observatory, and the European Extremely Large Telescope, will capture images of galaxies like Hoag's object with unprecedented clarity. These instruments will allow scientists to resolve fine structures within the galaxy, distinguishing individual star clusters, mapping gas and dust, and examining stellar populations in exquisite detail. This scrutiny can reveal whether the galaxy's ring is composed of younger stars from recent gas accretion, or if it's made up of mainly ancient stars, suggesting a different formation process. Spectroscopy, a key technological tool, will also play a crucial role. By analyzing the light emitted or absorbed by different regions, astronomers can determine the chemical composition, ages, and velocities of stars and gas. These measurements help reconstruct the galaxy's history and infer formation processes behind its distinctive ring. For example, if the ring's gas shows signs of enrichment with elements produced by older stars, it might indicate an internal process or a past merger event. Conversely, low metallicity could suggest accretion of pristine intergalactic gas. Precise stellar motion measurements through spectroscopy will also shed light on the galaxy's stability, whether the ring is a long-lasting structure or a transient feature resulting from interactions. In addition to optical and infrared observations, advances in radio and X-ray astronomy will open new horizons. Radio telescopes, such as the Square Kilometre Array, will probe cold, neutral gas that fuels star formation, revealing hydrogen gas distribution within and around Hoag's object. Detecting faint gas streams or structures could provide evidence of external influences shaping the galaxy. Similarly, X-ray observatories can detect high-energy phenomena, like activity from a central black hole or remnants of energetic past events, that might influence its dynamics or formation history. These multi-wavelength observations give a holistic view, integrating different aspects of the galaxy's life cycle and environment. Another transformative development is the use of adaptive optics, laser guide stars, and interferometry, which greatly enhance ground-based observation clarity despite atmospheric interference. These technologies will enable high-resolution imaging from Earth with clarity comparable to space telescopes, but with greater flexibility and potential for larger, more powerful instruments. The synergy between space and ground-based systems allows continuous, detailed monitoring of galaxies like Hoag's object over time, capturing their evolution and dynamic processes in real time. Future observational techniques like gravitational lensing also promise breakthroughs. By studying how light from the galaxy is bent by intervening mass, scientists can map unseen matter, potentially dark matter or other exotic components, within and around the galaxy. If Hoag's object's ring is influenced by unseen gravitational effects, lensing could reveal hidden mass concentrations that challenge current models. Advances in computational power and data analysis, including machine learning algorithms, will handle the enormous datasets generated by these telescopes. These tools will automatically identify subtle features, anomalies, or patterns that might otherwise be missed. For instance, machine learning could detect faint structures or trace stellar movements over decades, providing insights into the physics involved much more efficiently than manual analysis. Ultimately, these technologies are about transforming raw observations into comprehensive models of galactic formation and evolution. They allow testing different hypotheses about the origins of rings like Hoag's objects, whether they result from ancient collisions, internal dynamical processes, or more exotic physics involving dark matter or modified gravity theories. The synergy of advanced telescopes, multi-wavelength observations, cutting-edge imaging techniques, and computational analysis will peel back the layers of mystery surrounding these cosmic oddities. They will enable us to connect the dots, understanding how such galaxies form, why they remain stable for billions of years, and what they reveal about the fundamental workings of the universe. Each new discovery brings us closer to unraveling the cosmic puzzle that Hoag's object represents. A universe full of surprises that challenge our understanding of physics, logic, and beauty beyond imagination. Can simulations help recreate the formation of Hoag's object? That's a question astrophysicists grapple with, and the answer is both promising and perplexing. Computer simulations are essential tools in exploring the cosmos' elusive phenomena, offering insights often impossible to glean through observation alone. But when it comes to a galaxy as enigmatic as Hoag's object, simulations encounter critical roadblocks. Imagine crafting a virtual universe from scratch. Input initial conditions, test physics, and see if the cosmos can grow into something resembling Hoag's object. This approach has been used for decades, but Hoag's object presents a particularly tough challenge. Its near-perfect ring and central core, both made of stars and gas, seem too precise and symmetrical to have formed naturally within regular galaxy evolution models. Traditional simulations rely on known processes, galaxy collisions, accretions, dark matter halos, but they often fail to produce such extraordinary structures. Replicating its pristine, symmetrical ring is especially difficult. Most galaxy formation scenarios involve chaotic events, collisions, gravitational interactions, turbulent gas flows that tend to produce irregular, asymmetric structures. Simulating a perfect ring requires finely tuning initial conditions with exceptional accuracy. Small deviations usually lead to warped or distorted rings or entirely different shapes. Achieving Hoag's object symmetry suggests either an unlikely coincidence or some unknown stabilizing physics. Another challenge is how such a ring persists over cosmic timescales. If it formed from a collision, signs of past interactions, disturbed gas, stellar streams, merger remnants might be expected. Yet, observations show a calm, isolated galaxy. Simulations trying to recreate collision scenarios often result in chaotic structures or cause the ring to dissipate over time. Its stability hints at unknown physics, perhaps alternative gravitational effects or unseen components, that preserve the ring's structure rather than dispersing it. Star formation within the ring adds further complication. The stars are older, redder, and more metal-rich than those in typical galaxy disks. Simulations that model the formation of such a structure must accurately depict complex gas dynamics, cooling processes, and star formation rates, each governed by physics that remain incompletely understood. If the ring formed through specific processes, such as slow, frictionless accretion or mysterious angular momentum transfer, recreating these conditions is daunting. Despite these obstacles, simulations are invaluable. They let scientists test hypotheses about different formation mechanisms, whether a head-on collision with a smaller galaxy, resonant interactions within a dark matter halo, or the influence of unknown forces. Some promising models involve off-center collisions or internal dynamical instabilities producing ring-like structures. However, matching Hoag's object's exact properties, size, symmetry, longevity, has proven elusive. The galaxy might be a cosmic anomaly, challenging existing physics. If simulations consistently fail to reproduce its features, it suggests our understanding of galaxy formation is incomplete. Perhaps unknown physics or exotic matter stabilizes such structures against cosmic chaos. Alternatively, Hoag's object could be exceedingly rare, so uncommon that current models are not calibrated to include their formation conditions. Running detailed simulations with all potential variables, dark matter, gas dynamics, feedback processes, gravity, even speculative physics, demands significant computational resources and advanced algorithms. Slight tweaks in parameters can result in vastly different outcomes, like a cosmic Rorschach test. It's a slow process of trial and error, with hope that someday these virtual universes will converge on something that looks and acts like Hoag's object. Although simulations have yet to perfectly recreate this galaxy, they remain essential. They push the boundaries of knowledge, test assumptions, and raise new questions about cosmic stability and the physics of large-scale structures. With advances in computational power and a deeper understanding of universe laws, simulations may eventually unravel the mystery of Hoag's object, revealing whether it's a product of familiar forces under extraordinary conditions or an indication that we've only begun understanding the universe's most mysterious structures. Studying peculiar galaxies like Hoag's object presents numerous challenges that challenge astronomers' understanding of cosmic mysteries. Their rarity and uniqueness make them difficult to find and analyze in detail. Unlike common spiral or elliptical galaxies, objects like Hoag's are so unusual that each discovery feels like unearthing a rare gem. While finding these galaxies is exciting, detailed analysis is often limited by their scarcity and the difficulty of gathering sufficient data. One major hurdle is the vastness of space. These galaxies can be millions or billions of light-years away, placing them beyond the reach of our most powerful telescopes for resolving fine details. It's like trying to examine a tiny pebble from thousands of miles away. The farther the galaxy, the harder it is to see small-scale features. High-resolution imaging is essential but challenging. Obtaining detailed images requires more observing time, better equipment, and advanced data processing. Resources constrained by funding, telescope availability, and technological limits. Understanding their stability over cosmic timescales adds complexity. These galaxies display remarkably symmetrical, stable structures, often described as a perfectly balanced spinning top, despite potential chaos from gravitational interactions, dark matter fluctuations, or past mergers. To decode how they maintain stability, astronomers rely on static images, modeling, and simulations since they cannot observe these galaxies over human lifespans. Indirect methods help deduce their evolution, but depend on assumptions that could be flawed, introducing uncertainty and complexity into interpretations. Environmental factors, or the lack thereof, complicate studies. Many such galaxies, including Hoag's object, are isolated, far from other galaxies that could influence their shape through gravitational interactions. This solitude makes their formation puzzles more intriguing, but also limits understanding because classical models often involve galaxy mergers or encounters. Without neighboring galaxies in action, astronomers are like detectives with only snapshots in time. Reconstructing history relies on limited data, making the understanding of their origins and evolution more difficult. The stellar populations within these galaxies pose additional hurdles. Deciphering their luminosity, composition, and distribution requires spectral analysis, examining light emitted by stars and gas. Dust obscuration, faint signals, and the need for multi-wavelength observations from radio to X-ray complicate this task. Each wavelength provides different insights, but integrating all data into a comprehensive picture is difficult and demands sophisticated technology and analytical techniques, pushing current capabilities to their limits. Perhaps the most fundamental challenge is that these galaxies challenge existing physics and models of galaxy formation. Every new observation raises more questions than answers. They force scientists to revisit core assumptions about dark matter, gravity, and the nature of matter and energy in the universe. These cosmic curiosities often lead researchers into unexplored theoretical territory, where